I guess, when we do our first break at 11, and it's just, what's that? Yeah, 11. And just right out here, right? They're cleaning it up. That's what I saw. They're raking up all the leaves. So I assume that's correct. So, oh, I have to be quiet. Oh, whoa, whoa. Okay. I don't know. Any comments, questions, doubts, criticisms? Okay. I'll try not to use foul language. Alejandro says that I would get boycott. What do you say? Eliminated from the? Okay. No, off of YouTube. Okay. I guess let's use it 5 now. 9:05. Okay. So I think we had already notified everybody that we were going to switch. That Adriana is not going to. You're not going to do your parameterization talk, but your other one, right? So I'm going. The reason why was they wanted like a little more introduction to the North American monsoon. That was what I did the other day. So today I'll do what my original talk was. I've added a couple things considering what our colleagues have talked about to make it a little more co-joined, or I don't know, a little more consistent. So I will talk a little bit about parameterization. Obviously, I don't have time to do it either. Convective parameterization in particular. Okay, so again, you can ask questions in the middle or wait till the end. I'll try to be fast. There'll be some similarities with what I talked about before. But anyway, so what I wanted to just first, there's a lot of people I need to thank, but it would take half my talk if I did that. But obviously, there's a lot of people that in Mexico I work with, Brazil, Germany, Portugal, a particular guy that I work with a GPS, a couple other people too. And then a lot of people in the US. Well, now I guess I could have said Italy, but I guess we don't really work together, right? Technically, we're doing it right now. Okay. Okay, so because of what I'm going to talk about, and my theme, so to speak, is the column water vapor, and it's been mentioned several times as a critical or an important variable in the atmosphere. Fairly simple, just the total amount in a vertical column that could, if you could condense it out, you could measure it in liquid water at a certain millimeters or inches depth. Okay. So I'll just talk a little bit about the science questions, and one of the things that I wanted to do was how we use this valuable variable to propose to modeling types or theoretical types. Okay, use this and show us that what you propose is consistent. Okay, we'll talk. We've talked directly or indirectly a lot about this. It's inherent in a lot of the things that we do. So I'll go about that. And then I'll talk a little bit about the parameterization, particularly the Arakawa and Schubert quasi-equilibrium idea, and some of the theories that cover this theme. And then one of the things that was, and actually Adrian has probably worked in this one a lot over time, is one of the problems models has is dealing with the shallow to deep transition. As you have you have no cumulus, little baby cumulus, and then they keep growing and growing up into organized systems. That's a very difficult thing to model, if you think about it. Okay. This I talked a little bit about the other day, the propagating convection, and then something, I don't know how much Arturo talked about it yesterday, but I'll put in my 2 cents worth. Okay, so what GPS meteorology said, GPS, what does that have to do with, here's my car, it says turn right on Insurgentes, and it's because you have a specific location. What does that have to do with water vapor, right? That seems kind of strange, right? Okay, so basically there's all kinds of satellite constellations in orbit now. There's the Russian system GLONASS, Chinese Beidou, Europeans. Actually, I think even maybe India is trying to set one up now too, if I'm not mistaken. Okay, so here's the basic idea. I'll go through this real quick. When the satellite sends its signal, in the signal itself comes the information about exactly where the satellite is in space, and they have these atomic clocks, so it's super, 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 super precise in terms of time. Okay, and they send it through the ionosphere. That causes a delay in the signal that has to be corrected for. That one's kind of easy, so to speak. But then when it gets into the atmosphere, that's a lot more complicated. Okay, so basically, obviously what we're interested in, once they eliminate the ionosphere, they make the ionosphere correction, okay, which actually is an area of interesting study, not what I do, but what we have to do is calculate, we see how much the delay is, and then we say, all right, what contributed to that delay? Okay, we know the total mass of the atmosphere, that's going to contribute something, but in particular, water vapor, because of its behavior in terms of the microwave signals, that can have a particular effect, a unique effect, so to speak. Okay, so we calculate what's called the dry delay, and then the wet delay is the difference. Okay, and from this wet delay, we can calculate the total water vapor. In there, we use some kind of standard parameters and measures to do that, and it ends up being very accurate. Okay, so basically, how we do that is we get this what we call the neutral delay. Separate that out. If we measure pressure at the surface, that in principle gives us the mass of the atmosphere. Okay, we assume, as we've done several times, that the atmosphere is basically in hydrostatic balance, which it certainly is at larger scales. Okay, and from that, we can pull out what we call the wet delay, and then this is where I was telling we have a couple parameters. We use a temperature, and it actually gives a profile of temperature. This is based on latitude and elevation, just kind of a little model thing. And then from that, we can get the precipitable water. And we can basically get precipitable water every 5 minutes. And the good thing is also that it's essentially all weather. It only in really, really heavy rains, like the hurricanes and things like that, does the signal get so messed up that it's a little bit harder, or a little more difficult. But in general, with clouds and even a bit of rain, it's not a problem, unlike different types of satellite measures, or even radiosondes going up through a cloud gives you a very different measure. Okay, so when the value I'm going to talk about, take that into account, the scale, okay, because that is obviously important. If you assume a scale height, I think it's fairly accurate, about 2.5 kilometers of water vapor. The atmosphere has, 7 to 8. The water vapor is typically about 2.5 as a scale height, okay? And then what you do is you say, okay, basically what we do is we typically throw away the angles of the satellites when they're really close to the horizon, because you have a lot of blockage and distortion and other errors, and just, okay, we get rid of those. So if we just make an assumption that, all right, on average, it's about 30 degrees, and we typically see about 10, 11, 12, just of the GPS, that's the US one. If you include all the others, it's actually quite a few now. Okay, like here's the idea, bunch of different systems that you can use, constellations. Okay, so if we do that, basically you can kind of think of the cone of view. What we're looking at is about 20 kilometers. Okay, that's our representative spatial value. And like I said, we get every 5 minutes. Okay, so all the things that I say here, keep that in mind. Okay, so me in particular, particularly in the last, like I'd say, about 15 years, I got into GPS through my colleague, Rob Kurzynski, who actually, he works with oscillations. He was at JPL and NASA for many, 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 many years. And basically he works, I don't remember if you knew him. You didn't know, Rob? Okay. So he basically works on what they call radio occultation, and that's satellite to satellite, and that also has a delay due to water vapor, for example. Okay. And then I've done a lot of measurements and campaigns and stuff like that. In particular, when I first started, when I was doing my PhD dissertation and stuff like that, I was working on convective parameterizations, or at least the theory behind them. Actually, very simple type models, idealized. And then later, as I came along, I started working on the GPS. And the first place I really started doing it heavily was in the Amazon. And then I've been doing it in Mexico now for a while. Okay. One of the things I would say that kind of motivated me is I'm not very good at this. Okay. Is the evolution of convective events. You already saw that from my previous talk. Okay. And what I'm motivated by in particular is to understand why models, or I don't want to say why models necessarily, we know why they have problems, no, but can we estimate, can we help better models? And in particular, like I said, Adrian probably worked on this a bit too, was this idea of the shallow to deep transition. That's a really hard thing for models to capture. Well, I should say capture is not the right word, to reproduce or to produce, okay? And so we set up, like, again, I've already talked about this a little bit, but I'll use some other examples today for this talk, okay, about the networks that we set up in the central and the coastal Amazon. And then also we've set up some in northwestern Mexico, southwest US. And this is related to a bit to what Arturo was talking about yesterday, okay, which is, this is actually a really big theme. Oops. Where am I going? Did I do something wrong? Oh, no, but why is this? Oh, okay. I say, why is this not working? Okay. So anyways, one of the issues here, and I don't know how many of you are particularly interested in it, but it's a very, very big issue, is how does I talked about it a little bit with respect to the Amazon, but how much of the moisture, either from the surface or the vegetation, is actually recycled into the atmosphere and helps produce or intensify convection. That's also a very difficult, remember my argument from my last talk was to say, hey, look at how complex continents are compared to ocean, where most people have developed theories and actually use baseline model calculations, et cetera. Okay, so the first thing, let's talk about, this will be my very brief introduction into parameterization. When I say parameterization, do you understand the idea, what we mean? Specifically convective parameterization, because there's many, many types of parameterizations and models. The basic idea is that because of the spatial and temporal resolution of a model, there's certain phenomena in the atmosphere that you can't capture directly. So you have to account for it indirectly. So for example, you cannot say, oh, convection doesn't exist, it's not important, don't worry about it. Okay, it's just radiation model, and that's it. Okay, well, that's obviously not true. Originally, when models started, they had 500-kilometer spatial resolution. You're saying, that's pretty huge considering the size of cumulus clouds. Okay. Now, through time, we've gone down to very, very, and actually now people even talk about what they call convective resolving models at the global scale. And I think you mentioned this, Spencer. So there's people whose initials, for example, are BS. I know. Okay. Apparently you guys don't get the joke, but I won't say anything vulgar. But no, the idea is now that you got global models that are resolving down at kilometer scale. That is so costly in terms of computation. And okay, I don't want to say these people are bailando, but what happens eventually? Okay, now I got 1 kilometer resolution. How do I resolve microphysics? We're getting down close to molecular scales. So you're always going to have parameterization. You can't say, oh, microphysics is not important in convection. That's not important. Well, it's actually probably the most important. Okay. So anyways, so basically what happens is you have to describe the phenomenon, convection, at the large scale in terms of some process to particularly certain variables like pressure, temperature, humidity, and you say changes in those represent what convection did. at that scale. So if you dropped 10 degrees or up 5 degrees or something like that, you attribute it to convection. Now, you obviously have to define some type of relationship. It's not just arbitrary. Okay, so that's what the convective parameterizations are, and particularly the quasi-equilibrium that we've mentioned many, many times already in the talks. Okay, it's kind of a motive. I would say it's actually behind almost all the parameterizations that are still used up to this day. Okay, one of the things that it depends on in particular is what we call timescale separation. Okay, the large scale process, and when I say that, you can think of like radiative cooling. That's okay, that takes actually just on the order of 10, 15 days, something like that. But you can think about waves, what Alejandro was talking about the other day, that can change the profile and temperature in the atmosphere. But those are also on the scale of maybe of days or longer. But convection, as we've already seen, is on the scale of hours, even in some respects at the very small scale, minutes, but okay, hours to a day or so. So somehow you relate this scale of 7 days, 15 days to what happens at in a couple hours, okay? So you're not going to be able to resolve it directly, so you parameterize. Okay, so the idea of quasi-equilibrium is that convection reacts very quickly to adjust to the forcing at larger scale. Okay, so the forcing creates instability in the atmosphere, and I think you talked about that, Simona. Okay, and then the convection reacts to get rid of it. Okay, get the idea? All right, and actually, just even going as basic as this, there's some serious issues also about the original idea of scale separation. Okay, Brian Mapes had some arguments as to why that might not be a very good reason. And then we had a little battle with Jun Ichiyano. Yeah, if you want to see that one, it's a very small article. Arakawa and Schubert, when we were doing this work, it has 158 equations in the article. 158 equations. And then there's like a sub area to what do you call it? Like a appendix. That was not fun. Well, I shouldn't say it wasn't fun, but man. Ugh. Okay, so there's also the idea that, okay, once you have this instability that's generated in the atmosphere by the large scale forcing, and then convection reacts, well, what does it set the atmosphere to? What kind of temperature profile? What kind of humidity profile? That's really hard, okay? What is the quasi-equilibrium state? That's taken out, pushed back, taken out, pushed back. Okay, how you actually measure it, now this was also another kind of argument, and I wasn't involved in this, okay, but what is you remember what the moist adiabatic, did we talk much about that? I think I mentioned a little bit, right? Did you mention it? Yeah, okay. So basically, what the idea here is that if you have a certain parcel or a certain condition in the boundary layer, that will determine what the temperature profile is through the moist adiabatic adjustment of convection. Okay, very simple idea. But what this argument was here with Earl Williams, who's at MIT, and Milton, who was my advisor, was they say, hey, you guys Kerry Emanuel's calculation is a little too neutral, too soft, because he makes certain assumptions about the thermodynamic process of adjustment, reversible adiabatic particularly, okay? Now, one of the things, and this is where I come a little more into the picture, really the idea of how the water vapor vertical structure is in quasi-equilibrium, that's unclear. But as you saw from my other talk, and I would say even indirectly through our colleagues' talks, the actual structure of water vapor horizontally and vertically is critical. Okay, so here's the idea, again, kind of schematic-wise. I want to thank Kathleen Skiro. She gave a talk here. They gave a little course kind of like this. I don't know, was it about 7 or 8 years ago? I don't remember. She and Ben Lintner. And so I stole some of her figures because she's better at it than I am. What was that? 7 years ago? Okay. Anyway, she's great. She's at University of Virginia in Charlottesville. Okay, don't know my geography anymore. All right. So anyway, so here's the idea, here's a picture of what I was saying verbally, that you have a single point And somehow you have to represent all of these processes. That is the behavior of convection, moving mass up into the atmosphere at a certain velocity, things like that. That's going to depend on the nature, the size. This is hard detail to get to when you're only resolving one point. Okay, but you have to account for this. You can't get away from it. Okay, and that's where parameterization comes in. Okay, so here's like another schematic I think is good. So basically you would argue that you have some kind of neutral, or I should say quasi-equilibrium curve. Okay, some large scale forcing like a dynamical forcing, a mesoscale system, or even larger wave that can change kind of the vertical structure of temperature or even water vapor convergence, that forces the atmosphere away from this kind of neutral or quasi-equilibrium state. Then you get convection and bonk, it drives it back very quickly. Okay, so the scale of this forcing again is on it's larger spatial and larger time scale. Okay, bonk, go back and forth. Okay. So that's the basic idea verbally would be that convection acts to reduce buoyancy, what's called the cloud work function in the Arakawa-Schubert scheme. Okay, it's a very fast time scale, and the driving or the forcing, large scale forcing, is very slow. Okay, cooling the atmosphere, warming, moistening, boundary layer, blah, 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 all the things I've already said. Okay, and then there's other types of versions of parameterizations. Okay, so the cloud work function, Arakawa and Schubert's cloud work function that's actually used inside the model to parameterize convection is basically CAPE, okay? And what it depends on, what they're calling lambda here, is entrainment. And it's been mentioned again a couple of times, and that's basically as the cloud goes up in the atmosphere, it mixes with the atmosphere. And that obviously changes the characteristics of the cloud. Okay, the quantity of water, liquid water, temperature. That's a huge issue also. Okay, and actually Kathleen has an interesting paper, I don't know, maybe 2 or 3 years ago now, maybe less, I forget, where she looks at convection in the Amazon, and she argues for a certain type of entrainment based on the flow into the clouds, into the mesoscale systems. I'll send it to you guys if you're interested. But anyway, so if you have a plume, you know what I mean when I say plume? Get the idea of plume? So like in fluid dynamics, you have different forms of air moving, and a plume would be something that kind of starts at a single point, almost like a cone shape. That would be considered like a plume. Like a smoke plume, look at going out a chimney. That's kind of a plume-like thing. Okay. So that's think of it, you actually have to model the nature or physical nature of the convection, okay, or something that represented. Okay, and so when the plume has no entrainment, the work function for that no entrainment is basically CAPE, and they're saying no dilution here. Okay, and so there's a relationship between, remember what does CAPE do? That's convective available potential energy, and that can be converted into what? Starts with a K. Has to do with motions of things, like movement, vertical movement. KE. Okay, we're in. Very good. Okay, so that's kind of the idea. That would tell you something about the intensity of convection. And there's other different, you have like dissipation and stuff like that. There's other things you have to account for, but don't worry, just get conceptually the idea. Okay. All right. So I'll basically, like saying here, convection and model depends on some kind of assumption regarding the interactions between convection and the larger scale. That's the idea, no? And what I said earlier was that most convective parameterizations, either directly or indirectly, have their roots in the quasi-equilibrium, and most of them are kind of buoyancy-based, buoyancy being the CAPE, okay, for example, okay? And so basically what happens, also important, using the virtual temperature here, that includes water vapor, okay? And you have the environment, okay? You can use temperature and stuff like that, but it's a little simpler, okay? But so you have either, going up like a moist adiabat, dry, and then you've already seen this several times. Okay, so again, basically you had to take care of, we talked about here also the heating and the moisture profile. And these are all kind of the things you have to consider when you're making these calculations. But the important thing here is you have to have conservation of mass. Okay, and that's what they mean by this closure. Okay, the mass comes up. How does it heat the atmosphere? Adrian mentioned this. I think we mentioned it the other day. How does, on the global kind of Hadley cell kind of Simona scale, how does convection heat the atmosphere? Through what mechanism? You have to have conservation of mass. What does it force? Large scale, global scale. Rises up. Does it go to Mars? No, it's conserved. So what happens to all the air surrounding it? Goes down. We call subsidence. That subsidence, quotes, heats the atmosphere, and what happens to that heating? It's radiated out to space. Okay, first order kind of idea, right? Okay, so that's the function of convection, so to speak. Okay, now, really, in what Arakawa and Schubert were also kind of thinking about is really kind of tropical. You know, when you have very strong frontal systems and things like that, well, the dynamics are a bit different. So you can't really, the logic, let's say, doesn't necessarily apply as easily. Okay. Okay, so what I want to offer, and again, like I said, I talked a bit about this on Monday, is let's take a look a little more detail. Obviously, again, no time, but we'll go through a little more detail, and I'll look specifically at two theories. Okay, what's called self-organized criticality and thermodynamic control. Okay, in the self-organized criticality, you can kind of, it's basically thermodynamic kind of statistical physics. Okay, I'll describe a little bit of the idea here. And so it's very straightforward in that respect. It's just a column water vapor based on thermodynamic processes in the grand scale of things, grand scheme of things. And then Raymond theory is a little, I would say a little more complete in that there's also mechanistic things that are taken into account. Okay, so all these ideas, and they're begin basically for the tropics. Again, we're all over oceans. And again, that makes life easier because you have a very homogeneous surface. Okay. Somebody say something? Oh, Jorge, sí. Son exactamente homogéneos. Ni cambian ni un centímetro, ni un grado, nada. Okay. Entonces, we have to eliminate somebody from the auditorium. Okay. It depends. I mean, it depends where you're coming from, right? To me, it's entirely homogeneous. So other people's is not. Okay. So take a look here. All right. This idea of the relationship between tropical rainfall and column water vapor or precipitable water vapor goes way back. Okay. I'm certainly not the first person to suggest this. Okay. For example, Chris Bretherton, Xubin Zhang, there's quite a few actually. Like, again, like if you're interested, I can pass you the studies, but they all tend to have this kind of ramp up behavior. Okay. Usually particularly at some kind of critical value. Okay. And I think that's the Indian Ocean, West Pacific, East Pacific, Atlantic. And they say, oh, okay, well, it's fairly consistent in the tropical regions. Okay. Precipitation as a function of column or precipitable water vapor. Okay. Now, particularly in Raymond's theory, okay, he has kind of two fundamental assumptions. Okay. He argues that precipitation is a decreasing function of the mean saturation deficit. Okay. He assumes, and we've talked a little bit about this also, that the temperature profile, particularly in deep tropics, is essentially constant, which it essentially is, certainly compared to Minnesota or Canada or something like that. Okay. And I mean, he has a couple different theories, what he calls kind of boundary layer quasi-equilibrium. And so basically in that one, he argues that the drier middle troposphere gives up less updraft mass flux for a given entropy flux. Okay, can't go into all the details here, but so his basic idea. Now he says saturated fraction, and you could say to yourself, "Wait a second, I thought Dave was talking about precipitable water vapor." Okay, so what do you guys understand for saturation fraction? Any ideas? Basically, if you take a temperature profile and you say, all right, at that pressure and temperature, what's the saturation value? Okay, and how far am I away from it in actuality, my actual specific humidity, things like that. Okay, if you integrate that value, that the lack or the difference between being saturated and the actual amount is the saturation, okay, fraction. And then so that still doesn't answer my question that I said to myself or to you. How can I say that's related to precipitable water vapor? Why am I saying they're kind of the same things? Well, because in the deep tropics, we assume that the temperature is not changing in space and very little in time too. Okay, so basically it'll have the same behavior. And actually, look, it does. This kind of ramp up. Okay, fully saturated, totally dry. Okay, as you get up higher in the saturation fraction, which means you have more column water vapor, boom, you get this ramp up. And these are from different campaigns that were done past. Okay, now the self-organized criticality idea. Like I said, this basically kind of comes from statistical physics, and it's actually used in a lot of things, including even human activity, traffic, book purchases. You can use this idea in a whole lot of things. It's a criticality idea. Okay. And basically it refers to a certain type of, you can think of like a certain type of statistical distribution. Okay. And I guess we haven't actually talked about it so much so far. Precipitation tends to have kind of a long tail distribution. It's not normally distributed. You have a lot of high quantity or frequent low value precipitation and very few extreme values. Okay, so it has that kind of, could be maybe like an exponential fit or gamma or one of these different statistical distributions. So the idea here, and like I said, this is a slide from Kathleen, her presentation. So basically the idea is you slowly drive the atmosphere, again, using the language of self-organized criticality, a highly susceptible system that can store energy, for example, in the form of water vapor, and then suddenly releases it as rain showers. Okay, so you build up energy, bunk. You release it real quickly. Slowly driven, then you have convection and you release it. And then it goes back to kind of this critical state. Doesn't that sound a little bit like quasi-equilibrium theory? Isn't that kind of what I showed on the other slide, that you force the atmosphere away from some, stable equilibrium profile? I mean, stable in the sense of near that. Okay, drive it away and bunk, come back. Drive it away, come back. So there's an analogy here. Okay. Oops. Okay. So the self-organized criticality in the atmosphere. Okay, quasi-equilibrium refers to a balance between large-scale driving processes and a rapid release of buoyancy by moist convection. There is evidence that the attractive QE state is the critical point of a continuous phase transition. When I say continuous phase transition, do you know what I'm talking about? Think of, like, for example, when we always just think about water vapor, that's the center of the universe. So you have it at a certain temperature and pressure, and then maybe if you cool it, it turns into ice. It's like black and white. The continuous phase transition occurs at really, really, really high temperatures. Okay, and there it's a continuum. There's no physical change in the state that we would think of, like liquid to gas, liquid to ice, things like that. It's a continuous. Okay, that's, again, like I said, this is all kind of statistical physics stuff. Another phenomenon that, important here in Mexico City, and I guess in Colombia too, are earthquakes. Okay, they tend to have these kind of distributions. So you only get like really strong earthquakes every once in a while, but you get a lot of little tremors, right? Is that what we say? I forget English. Tremors, right? I used to speak English at one point in my life. Okay. So that's the idea. So basically, Peter and David Nealon, whose name keeps coming up day in and day out and day in and day out, I think it's more Peter's that came up originally with the idea. But Jake, we can say, all right, that's a kind of the quasi-equilibrium, maybe according to the kind of Arakawa and Schubert idea, is really a critical state, a critical point. Okay, so what do I claim? I claim, hey, well, let's take a look at our GPS data and see, is that true? Is it consistent? What do we see? Okay. Okay, so here's like I said, a schematic. Okay, so basically, this is how. So in other words, if you claim that self-organized criticality represents this kind of quasi-equilibrium behavior, you have to have this kind of distribution. Okay, it's got a little bit of rescaling to it. Okay, but you can think of it as column water vapor here. Okay, it goes up. And this is the sigma squared is its variability. And this black line, okay, is what we call kind of the critical point here, the critical value. Okay, so the critical value has to line up with the maximum in variation. Okay, that's what these that's the behavior of a self-organized criticality system, for lack of a better word. Okay. And they have their names, order parameters, susceptibility, et cetera, et cetera. Okay, but the important thing is you have to have this kind of behavior. And what's interesting, again, part of the idea of theory, is that you get these constant, what they call beta, a universal constant. Okay, and if you plot it on a log-log plot, it's linear. So that's another behavior that has to be observed. Okay. Okay. And again, I said, like, I have all these papers, so if you want them, send me an email. Okay. All right. So going back to my stuff, you already saw this the other day, so I'll just go quickly. I've got about four years or so of data from Manaus, and then we had our experiment in Belém. Okay, here's the idea: 3.5 in Manaus, the dense network, and then we were part of the Chuva campaign. In 2011. Okay. All right. Now here's where I set up our the one long-term site. Okay. And what was interesting at this point, my colleagues at NOAA actually processed the data near real time, which was kind of cool on their part, and they didn't charge me anything. That was nice. Okay. And this is centered at the LBA, which is the National Research Institute for the Amazon. They're still, and the LBA was originally a large international experiment, but it became a federal program in Brazil. Okay, so basically we had about 3.5 years of data. Okay, there's the antenna there. Okay, Vaisala. You guys seen one of these things before? Okay. Actually, it has a strange way of measuring precipitation. It's by impact. So it's not the most accurate, but it's not too expensive. Okay, so the question, all right, what does our GPS MET data using column water vapor show with respect to water vapor criticality? Okay, and this is a paper that we wrote with Kathleen, with David Nealon, and Ben Lintner. Okay, and actually it has a lot of citations. That's when you get to be part of a mafia. Oh, I forgot I can't say these kind of things. Okay, well, Jorge's not laughing, so he didn't understand the joke. Okay, so basically we took our 3.5 years of data, and what we did notice is that over land, remember I was making this argument that land surface continental values, you have to take that into account because oceans are completely and entirely homogeneous. Okay, so let's take a look at the behavior here. All right, does have that kind of ramp-up-y thing. Okay, the probability of the precipitation, a very similar behavior. And then we have our frequency density here. All right, does have that kind of maximum behavior. Okay, so if the water vapor or the self-organized criticality idea is true, then we would expect some kind of straight line up through the basically the variability. One other idea, I just wanted to throw this in. Jun Ichiyama was also interested in these ideas. He wanted to compare the self-organized criticality with Raymond's ideas. Okay, so he came up with this basic idea that, all right, precipitation, okay, in the self-organized criticality is constrained above a critical value, but the water vapor, column water vapor, is not. So it can continue to increase, as you see here. Precipitation is constrained to a certain value, and water vapor can keep going. In the Raymond idea, okay, criticality is constrained, or I'm sorry, the water vapor is constrained, but the precipitation can keep increasing. Okay. Okay, so there's, all right, that you should show up in your data, right? Okay. In what he calls it here is homeostasis. So you kind of think of like biology, that we have this ability to kind of take in a lot of little different things and we maintain ourselves around a critical value. That is our body temperature, digesting food, whatever. Okay. So this would be, like I said, analogous. All right. Another, I don't want to say, maybe criticism is the right word, but Gilmore, I think he was in Australia. I'm not sure about that. Do you know him? Do you know him, Adrian? No? Okay. But anyways, he argued that because precipitation, and what radiometer was another that Nealon and Peters and these guys used to make their criticality argument, he said, you know, this is all right, this is the behavior that you want to get, where you get this kind of peak value running through the peak of the variance, okay? But a lot of times you actually don't get it, okay? And what he basically argues is that if you have a lot of noise in the data, which means error basically, that you can tend to get this type of behavior. So it's more of a function of the error in the data than an actual physical representation of the process. That's what he argues, okay? I'm not trying to pick on Peters and Nealing or anything like that. I didn't want to make sure that's clear. All right. So what does our 3.5 years of data say? Okay. With respect to continuous phase transition, that is a self-organized criticality idea, ain't obvious here. Okay. We don't have our drop off of precipitation, okay? The variance doesn't drop off. And it's not peaked at the column water vapor that it should be. This is more in line with Raymond's arguments. Okay? Okay. So, and I would argue, because remember this Gilmore's idea, he said, hey, wait a second, it depends on what you use in terms of, you know, what type of satellite, if you're using TRIM, or if you're using radiometers, things like that to measure precipitation. And I would say, I mean, I've been saying that the GPS is more robust in rainy conditions. Okay, so this supports more Raymond than it does Peters and Nealing. Now, my co-authors were Nealing and Kathleen and Ben Lentner. Okay, so we argued a lot because if you read our paper, this was not included. Okay, and you can imagine, you've seen how I am for a couple days that I had to fight. And it was 3 against 1. Well, 2, 3, I don't know. So anyways, we left it out, and I think it was a reasonable argument. And I think it was, if I remember correctly, it was Ben said, look, your Vaisala apparatus also doesn't really capture the full range of variance. And that's true. Yeah, that's true. I can't really deny that. So, all right, we left it out. But we could, if we hadn't access, sometimes in Brazil, it's very hard to get access to other data. It exists, but it's just hard to get it. So we could have looked at this, but we just said, all right, time's up. We'll publish the paper. Okay, but it still needs to be investigated. And we're still doing Amazon stuff, so maybe I'll get my chance in the future. Okay. Okay, how am I doing on time here? I think I'm going a little slower today. Okay, so I have another 45 minutes. Okay. All right. So basically, now here's something that I've been pushing on a lot. Now think about, well, I guess it's not, more maybe Adrian, because he works a little more closer to the mesoscale and stuff like that. And Simone and Spencer are obviously a much larger scale. But again, what I've been arguing is that when you're looking at this kind of mesoscale, and we're talking on the day, less than a day or less in the order of tens of kilometers, maybe up to 1,000, but I mean, really on the very small scale, tens of kilometers, 1 kilometer, things like that. Okay. How this has been a challenging problem is to cover that evolution of deep convection from little baby cumulus to mid-sized congestus and then up to a big storm and rain, or even big storm, rain, and organization. That's even harder. Mesoscale convective systems. Okay. So what my basic approach, at least mathematically, where you would make these kind of simplifications. Okay. So you take the you take the water conservation equation. You make a couple of simplifications like ignoring the contribution of cloud liquid water. Okay, say that that's small on the time scales and things. Another simplification that we make is, I say, at least on the time scale of the shallow to deep transition, we can ignore the local evaporation, surface evaporation, and obviously precipitation we could ignore since we're trying to cover up to that point. Once precipitation starts, our theory, our idea ends. Okay, so did someone? I thought I heard. Am I hearing things? Okay. So basically, what I would argue to a first order, the time rate of change of PWV is simply moisture flux convergence, which is convection. Okay. And again, what scale am I talking about? I said that earlier in this talk, about 20 kilometers-ish. Okay. I'm sorry, what did you say? The what balance? I'm saying no. I'm saying I argue in the paper that the contribution is small. Ignore it. P, we stop. Once P starts, you're gone. So, see what I'm saying? So P is 0 in the sense that, hey, it didn't happen while we were doing this calculation. Uh-oh. Oh, okay. So yeah, read the paper. It's a GRL paper. Okay, it actually has a decent amount of citations, which is good. Okay, so that we make these arguments, you can see specifically how we do it. Okay, so again, models don't replicate in Betts and Jacobs. I think Jacobs is also from Australia, if I remember correctly. I don't remember. And it's actually motivated the LBA experiment in the first place, is to try to get models to be able, or parameterized convection, to be able to represent. Okay, and so here's something that I probably, again, Adrian might be more interested in these kind of things, is what actually controls the shallow to deep convection transition. That's still debated. Okay, you got many different things, and I'm obviously running out of time, but I can hand you all these different papers. Okay, one here was kind of interesting because Kairatynov, he's a Russian guy. He came here. Remember that? He visited us here, and we sat down and discussed some of his ideas. Okay, and then there's another one, Wu et al., and there's many, many more. But just so in other words, these have different physical aspects that say, hey, they're responsible for the transition. Okay. For example, I think Adrian mentioned this maybe 20 to 30,000 times. Cold pools, right? Okay. So you get precipitation, you have evaporative cooling, that forms these little cold pools, and they can crash into each other, and that actually gives you a little bit of a forcing mechanism. That was the argument basically of Kairatynov and Randall. Okay. Here's their paper, and what they argue at 11:30 in the morning to 5:30, moist static energy. Okay, Spencer talked about that a lot, moist as a critical variable. Okay, and what they argue is, okay, it's kind of random. You get the cold pools, and they converge, and that helps the shallow to deep transition. Okay, I have reasons why I don't agree with that, but again, you can ask me in coffee break time. Okay, so what we do, well, you think about this in our GPS site. Okay, we grabbed all of the convective events we could. There's a lot of them. Okay, so you have the change, time rate of change of PWV. Okay, you have cloud top temperature. That's something we use a lot, everybody here. Okay, and then some rainfall. Okay, and then our local met pack. Okay, you have basically wind and a strong temperature drop. That's a clear sign of, like, for example, a cold pool. Okay, but it also indicates, let's say, for example, it was raining really hard, but it didn't rain over your, your little Vizsla, but you saw this behavior, In the Amazon, this can only happen when it's raining. There's no other way to get temperature to drop and wind to increase at the same time without rainfall happening somewhere nearby. Okay, so we use that argument too. All right. Okay, so we had of the 3.5 years, we had 320 events. Imagine, that's a lot. It rains a lot in the Amazon. Okay, and what we came up with was this convective time scale here. Okay, here was the part we argued that maybe evaporation can be important. You couldn't take it out of the equation necessarily, but at this point in the ramp up period, this is what we call the transition, okay? This period, about 4 hour period, take a look. If, for example, if you think of the cloud liquid water as being important, that, hey, Dave neglected that, that's a bad idea. Take a look. Cloud temperature drops, that is, clouds are growing, and you have water vapor convergence. So obviously the cloud term is not that important, okay? Because if cloud term were important, this would go like this. Okay, so that's a GRL paper that I have with my colleagues from NOAA and one of my former Brazilian students. Okay, and then I've already shown this to you, but the reason why I do it is because we came up with another idea to look at the shallow transition, another metric. Okay, and what we did here was we used all of the stations, but only for 10 months or so, I forget. Okay, and what we came up with is what we call a spatial decorrelation time scale. Okay, so basically you have the fields here of deviations, like little deltas of PWV, 5 hours, 4 hours, 3 hours, 2 hours, 1 hour, 0, when the convection actually is intense and happening over our site. Okay, so what you see, the stations at this point right here are very highly correlated. They're all behaving the same. All right, makes sense. As you get towards 3, you start to get these contour lines where the behavior begins to deviate, become more intense and less intense. Okay, and then as you get towards the convective event, well, it gets very concentrated. Okay, so what we came up with is you get like an exponential function. Okay, and you can derive a time scale. Okay, so this is entirely independent of our other methodology, but if you take a look at the time scales, 3.7, 3.2, 3.4, all, so it's actually pretty much the same. So 2 entirely different metrics, but give more or less the same result. So our modeling friends, they should be looking at this and saying, okay, yeah, we can produce that. Our model does this, or at least for the Amazon region, okay? Okay, and then you've already seen this, so I won't. What I wanted to show here, I didn't show the other day, which I think is interesting. Remember we showed these squall lines that come in and penetrate from the Atlantic Ocean in northeastern Brazil, Belém? Take a look. I always thought this got my attention. It was also another point of interest of the LBA experiment. Look at how timely the precipitation is. It happens almost exactly at the same time every day. So that's kind of convenient. Okay. So they have an expression there in Belém, a gente se encontra antes ou depois da chuva. And I'm sure you can understand what that means, right? Should we meet before or after the rain? So that's their time scale. That's their alarm. Okay, and I think I showed a similar picture of these convective things. Another thing that, if you remember, I showed you the animation of days where if you form convective cells, lines along the coast, these are the days that actually penetrate and you get the rain in Belém. And the days where they don't form very strongly, they tend to be dry. Okay, and then this is what it looks like just looking at some of the ramp up, the diurnal cycle, so to speak, the ramp up. I've got another 20 minutes. Okay. All right. So here's this one I'll do real quickly too. I already talked a little bit about this, but what I wanted to do in particular was kind of refer to what Arturo was talking about. Something that's being debated again, moisture sources. That's, okay, we don't want to get into that one. Okay. Okay. Now here, you mentioned this, Arturo. Francina Dominguez. She's a good lady. She's Colombian. They're not laughing. Okay. All right. She's very nice. She's from Bogota, if I remember correctly, right? She's very nice. She's come here too and given talks and stuff like that. And so she has a very simple model. Well, I wouldn't say simple, but she argues, there's contributions from Atlantic, contributions from Pacific, and then she argues that actually the contributions from land is important. Okay. And we showed this the other day. It's pretty crazy. Okay, how green occurs so quickly. Okay, in one of our experiments that we did in Arturo, yeah, you participated in this too, right? Carlos? I forget. No. Okay. And so we installed receivers at different flux towers in different environments, very near Rayon. Okay, take a look. So this is basically latent heat, evaporation, and precipitable water vapor. Okay. All right, so over the whole season, and then over the high rainy period. Can you guys see a real obvious relationship there? I can't. If you guys can, please tell me, let me know. Okay, so just looking at Rayon, all right. Water vapor, latent heat flux. Okay. Take a look, most importantly, we made little baby climatology averages for Rayon, Opodepe, and Walnut Gulch, which is in southeastern Arizona. Take a look. I mean, you probably won't be able to see it real quick given the time constraints, but what you'll notice is that convective days and non-convective days have exactly the same, well, not exactly the same, but basically the same latent heat flux. So it's like, At least at these 3 sites and the other 2 or 3 sites that I've worked at and done, we have not seen a strong relationship, okay? And actually in Arizona, if you talk to the meteorology guys at the National Weather Service, they have an expression. It's too wet to rain. So that is, if the surface is really wet, it doesn't rain. Why? Think about it. Think about it, and we'll talk about it in the coffee break. Why doesn't it rain when the surface is really wet in Arizona? Okay. Now this is where I make friends. Okay. Some people here, I'm not going to mention names, have talked about using reanalysis data. Okay, let's take a look real quick. Here are errors associated with era interim. We compared it to a site in Badiraguato. I'm not going to say anything about that. Basasiachik, which is on the top. Look at the size of these errors. They're insane. Now the scale size, it's cohesive. You can't get this type of error. You can get a little error here or there because they're not exactly the same place, but you can't get errors of 10 to 15 millimeters? No, sorry. Imagine that you're trying to calculate moist static energy in the deep tropics and you have this kind of error entering your equation, no? Or your calculation. Lot of studies, particularly with these moisture transports and the recycling, they use reanalysis data. Again, take a look, that's scary. This is the error in percentage. 40% error. Is that okay among friends? Are we cool with that? You guys okay? I'll buy you a beer. Okay. Now, fortunately, since I'm being sarcastic and aggressive and all that kind of stuff, the ERA 5 is a lot better. It did improve relative to the ERA interim. Okay. I mean, there's still pretty large errors. You can see this one has to be biased high. They're not small errors, but they're not 40% either. So you have to take that into consideration, whether you use reanalysis to check your knowledge, whether you use them as, quote, observations, which they aren't. Sorry, I'm being too aggressive. All right. This relationship, generally true. This, I say the jury is still out. That's an expression in English, okay? You say that in England too? The jury is still out? Okay. Okay. It's more consistent with thermodynamic control than it is with the self-organized criticality. The shallow deep transition, a very robust 4-hour transition, okay? And I would argue that our sites are interesting for calculating the speed of propagation and stuff like that, no? No obvious results of local surface influence, vegetation influence. Okay, real quick. We have a monster of a proposal that we're sending to NSF, a beast called Convect, and it actually is related to convection and water vapor. Well, transport and local evaporation in Arizona, in a very complex terrain region, really, really complex, but like kind of like the Sierra Madre, okay? And basically you have hills, valley, big mountains, well, not mountains, it's a plateau, okay? And so you get very strange, well, I wouldn't say strange behavior, you get very unique behavior of the convection that forms, okay? And like I said, there's like 15 different groups, NOAA, NCAR, NASA, a bunch of different universities, actually, they're starting to really focus now, actually, you would like this, Arturo, they're starting to focus on the interaction between the surface and the atmosphere, okay? So, and also, I talked to Jorge about this, we want to make sure that we have students from here at the UNAM or from Mexico in particular participating in this, because we're also going to set up locations in northwestern Mexico. So it'd be good also to parallelly, is that the right word? In parallel, ask for money from CONACYT or whatever might be a possible organization. Okay, sorry. Okay, so I guess I don't have time for, we'll talk, all my questions you can ask in the break. Is that okay? Just because I'm sure I overwent my.
Perhaps one quick question.
No. Okay, yes. Oh, yes. Oh, one other thing before I forget. I am teaching my atmospheric convection class this semester. So I will touch on a lot of these themes, but in detail. Okay, so if it's postgrado, I don't know how many of you are in our postgrado, I don't remember. But if anybody's interested, I'm open, you can come in. I let anybody come in. I don't close the door to anybody. Got the guy that sells tacos out in the street. Doesn't matter if you can come in, no problem. Okay. Who's next? It's Adrian. Okay. So write down your questions and I'll answer them on the break. Oh, that's my thing there. No.
So what I'm going to be talking about in the next hour is related to this issue of convection aggregation. Convection begets aggregation, but in a very idealized sense. We did originally have something on convective parameterization. If you like, we can maybe insert a short introduction to that in the hands-on. I can find maybe 20 minutes and show a few slides on that if you want a bit more detail. Okay. So let's start here. So what is actually aggregated here, do you think? Does anybody have any ideas on this? This is, I think this thing is dying, the pointer. Yeah, no, okay. So does anybody have any ideas? This is actually aggregation of the Japanese beetle larvae. This is data from 1936. Okay, so convection aggregation became a topic of interest, in the last few decades, of course, but people were looking at aggregation and statistics of flora and fauna long before meteorology even became a big topic, a big field, should we say, in the kind of post-war explosion. So, in fact, when we look at animals, we get examples of, should we say, clustering, so schools of fish. We can get examples of regularity. So if we look at families of gorillas, they have their territory, and so they're actually regularly spaced because they basically have their own territories they command, or apparently polar bears are quite agnostic about other polar bears. They kind of just wander around randomly. So they have a kind of a random distribution. So we're going to be talking about these kinds of like aggregation and so on, but in the case of course, clouds and convection. Okay. So I kind of mentioned this topic in passing in the introduction to the convection lecture I gave on the first day. So there are basically many different mechanisms by which a cloud might encourage other clouds to occur in the nearby neighborhood, or equally may suppress. Like you think of the example of the families of gorillas. So one of the most important things is the influence of the convection on the radiative field. So for example, the fact that we have a cloud present, which is a black body, it changes the radiative transfer through the atmosphere and can change the spatial distribution of basically cooling. So that gradient in diabatic heating could, and in fact does, drive convergence in towards the cloud. Another important feedback is the one that Dave was talking about extensively in his previous talk, and that's the feedback with water vapor. So, you know, there's actually quite a lot of complicated aspects to this that we can consider, but kind of we try and boil it down to a single sentence. Convection moistens its local environment, and that makes it more conducive to future convection. That links very much into the plots that Dave was just showing, where we look at like the relationship between precipitation and water vapor. It's a kind of a two-way interaction that leads to that relationship. If we have moisture environments, we have lower tropospheric moist static energy. Also in the boundary layer, we have the effect of entrainment. When we entrain dry air into updrafts, causes evaporative cooling. It can kill off buoyancy in the updrafts. But in the same way, convection moistens its local environment. Okay, and I'm going to come back to that in a moment. And then, of course, although Dave says I've mentioned it a million times already, for the millionth and one time, there's also the impact of cold pores. I showed this cartoon on Monday where we have these downdrafts spreading out. And you remember I showed that picture from satellite where we saw the interior where the convection was suppressed. And then on the boundaries, we could actually have new initiation. So in that respect, cold pores suppress locally, but then on their edges, they're encouraging convection, which could actually cause clustering on the scale of the cold pores. And these cold pores can have very vastly different scales. I mean, this simulation here is very idealized, and I don't have a scale on the edges, but these are spreading out to the order of kind of 10, 15 kilometers. But when you have a large mesoscale convective system, organized convection with many, many updrafts, and we saw a very nice example of that from Christian's talk earlier in the week, those big systems have many sources for the cold pores, and those cold pores can spread out over hundreds of kilometers and have timescales where they last for several days before they dissipate. Okay. So to kind of come back to this water vapor, these are kind of very introductory things. We saw this cartoon earlier in the week, which was kind of an east-west transect, but they also saw a similar cartoon for a kind of north-south Hadley cell transect. Okay. And so what I do for just a bit of fun is kind of first of all remind ourselves that convection, remember, is it detrains saturated cloudy air. It's moistening its environment in a halo, but its net effect is to dry the atmosphere because we're producing precipitation. Okay, so convection dries the atmosphere, of course, but that drying is felt in the far field over a much larger area, basically the radius of deformation, because remember, as this convection goes up, it's like throwing a rock into a pond. If we throw a rock into a pond, what happens to the water level? The water level, of course, for the displacement has to go up. How does the pond feel that? It's through the propagation of gravity waves. And inside the gravity wave front, the water is slightly higher. So the same way when we have convection, we have propagation of gravity waves. And inside the gravity wave front, the air has subsided. So that basically, if you think in a single location, you've got a vertical gradient of water vapor. That subsidence is drying the atmosphere at a fixed height. So that drying, basically from the precipitation, is felt over a large radius as the air is moving down in compensating substance. Okay. but locally the atmosphere is moistened. So convection is increasing the variance spatially of water vapor. Okay. So if we take this plot, which Simona provided me, of basically the column integrated water vapor. So this is the variable that Dave was showing extensively in his talk. And this is just basically an annual mean. And the first thing we notice, of course, is that the high values are basically associated with the areas where we have a lot of deep convection. So along the ITCZ, lying just north of the equator here in the Eastern Pacific, the Western Pacific warm pool over the continent. And you can see the high water vapor associated with the areas where we have the most deep convection. And so this is a very poor plot of the GPCP rainfall. I've just quickly pasted on there. I should have replaced that actually before this lecture. I forgot to do that, sorry. And a cleaner plot. But if we look now, this is this height on the y-axis, and we're going from the South Pole here to the North Pole here. And Simona showed this plot as well. This is the relative humidity in her introductory lecture. Okay. And so this pattern, as she said, we can kind of see, if we take this cartoon for a bit of fun, this is the Bjorn Stevens cartoon, and I kind of squash it, and then I'm going to kind of shift it over and duplicate it. And then we kind of pop this up here. So this is where we had the most rain, and it kind of almost lies on top. You can see this is like just slightly to the north of the equator, the mean situation of the ITCZ. And this peak in relative humidity here is where we have the detrainment. Remember, we had, when we looked at the convection, we really have these kind of two principal modes, the kind of boundary layer or shallow trade cumulus that's kind of detraining at the lower level inversion. And then our other stable point of the troposphere is right up near the tropopause. Okay, so they're the two main zones where clouds basically stop and detrain. There is also a third peak near the freezing level where we have a minor, should we say, stability peak. And so the reason why we get this pattern is like this is close to where the convection is detraining, and in the subtropics where we have very little convection, the air is going down. You can basically think of these areas as the furthest away, where the parcels have to travel the furthest from their convective moisture sources. So if I'm raining here, I'm a convection event, the further away you are in the atmosphere, the drier you expect to be because you're further away from your moisture sources. Okay. So anyway, that's the reason why when we look at the kind of mean OLR, so this is a plot I've taken from Dennis Hartman's excellent textbook on global climatology, we can see that the areas in the globe where we have the most outgoing long-wave radiation are those dry areas, which are cloud-free and essentially dry, which is why they're referred to as the radiator fins by Pierre Humbert of the planet. They're the areas where we most efficiently lose heat to space. Okay, so this is a kind of a global annual mean picture of the water vapor, but of course, you know, as Dave was showing in his talk just before, the devil's in the detail. There's a lot going on when we actually look at the changes from day to day of water vapor, and we saw these very sharp changes in water vapor in his talk, sharp horizontal gradients of water vapor. So if we have advection of water vapor and we have a GPS instrument, you'll see these very sharp changes. And that's very clear when we look at this animation. So this is MIMIC version 2 data. So this is not ERA 5, but if we did plot ERA 5, it would look quite similar. As he showed, the kind of gross changes are actually pretty good, even if we have some small offsets and biases. Okay. And so this is just a kind of a zoom into a box in the Western Pacific, which we were focusing on in a paper, but I won't be talking about that today. The white patches, by the way, the white blobs are actually precipitation I've overlaid from GPM. So that's basically where the rain rate is over 8 millimeters per hour. So you can see that tucked inside these areas of high water vapor is exactly where the convection is going on. Okay. So now what I'm going to do is, you want to try and understand this, but I'm going to move to a context of very idealized, should we say, approach to looking at convection and convection aggregation. So some of the studies in the past, and this is really where I kind of, I started this in my PhD, was on this topic of very idealized simulations of convection in the tropics. And I kind of moved away for many years, but recently I've kind of gone back to looking at this again with a couple of PhD students. So what we're looking at the top is just a snapshot from a simulation. This is one by Caroline Müller. And you can see that we have the dimensions on the sides here of this simulation are on the order of a couple of 100 kilometers. Okay. And this is a model that's basically using a resolution on the order of 2 kilometers. So effectively, it's convective permitting. But as Dave says, of course, it still relies on a lot of parameterizations. When you're at 2 kilometers, you're not really representing any of that subcloud structure. Remember, I showed that aeroplane flying through a cloud, and we saw that beautiful structure. All of that detail is missing in these models. Okay. All of that turbulence at the cloud edge is handled by the sub-grid scale schemes for turbulence, which are very simple, usually first-order closures. So they're very simple schemes that handle this. So what we really see is really just the bulk properties of cloud. If I talk about parameterizations, in fact, these models really look like entraining plumes in terms of their updraft properties. Okay. So they have microphysics. They normally have a fixed lower surface condition, like a fixed SST, or they might have a land surface, or in some cases they use a slab ocean. And as I say, they have very idealized setups, and they have first or 1.5 order closures. Okay. So an example really is a canonical paper from the early 90s. It wasn't really the first. Bjorn Stevens also highlights some of the work that was made by Japanese authors. But I think this was really the first paper that drilled down into the mechanisms of what was to become a big topic of organization. And this was actually simulations conducted with a two-dimensional model. So again, just like the previous model here, we have radiative cooling, we have heating from the boundary, driving these clouds, okay, in this domain. But this is a two-dimensional model, so it was 700 kilometers. And on the right-hand side, what we see here is evolution of time in the x direction. And this is the the y-axis is actually the x of the domain. So you kind of have to turn your head on the side and imagine this is your kind of spatial dimension. Okay. Or I should have maybe rotated the plot. So what you see is at the beginning of the simulation, you have convection speckled everywhere. Okay. But what we notice is after a number of days, it kind of collapses into two centers of convection, and eventually one kind of wins out. Okay, we only have one cluster here because the domain is very small, it's restricted. So we have an equilibrium state with one cluster surrounded just by subsiding air. Okay. Now, if we look, this is a kind of slightly more recent, although this is still nearly 10 years old. This is a simulation that my PhD student Adisal Semi made. He's just recently moved to the States, actually. He's now at NCAR. And what we're showing here again are each column is just categorized to make things simple into basically moist or dry. Blue is moist, red is dry. And I've actually separated it into dry lower and dry upper, but don't worry about that too much. So the dark blue is essentially convective cores, okay? And then we have basically whether they're cloudy or clear here, illustrated by the dots, lower and upper troposphere, okay? So what we notice is at the beginning of this simulation, again, we have convection bubbling around everywhere. So you can imagine if this room were your domain and you're all convection clouds, you're kind of distributed pretty much randomly around the room, okay? But over time, you see there's a little dry patch emerge, okay? And then everything starts to cluster. It's like maybe, if Spencer suddenly decided he was going to give out $100 or something, we all kind of rush to the corner here. And then the rest of the room is empty, you see. So we can see the growth of this kind of cloud-free patch. And it also is becoming very dry. Dry because these points are now far from their moisture sources, okay? We see this behavior even in global models. So these are idealized setup runs. These planets are not rotating. 3 different global models, and you'll see that when we run them in radiative convective equilibrium, so the convective heating is balancing the cooling, again, we get collapse of the convection down into points. But what we do notice as well is that the nature of these organized states is very different from model to model. So remember, these are all using convective parameterization schemes. They have other aspects that are different. So, although we have clustered states, again, we have a situation where, we have very strong model dependence. And I think these setups are actually nice to kind of understand differences between models, because when you have strongly forced with like land configurations and so, it can hide a lot of differences between parameterization schemes that kind of jump out much more clearly when you have very homogeneous boundary conditions. Okay. So why are we interested in this clustering in these idealized states? Well, again, it kind of links back very strongly to basically, let me just close down the video here so I can see the screen. It links back very clearly to the sensitivity to climate, because if we have a random state at the top, okay, when we have random states on this here, this is our precipitable water. You can tell it's because I used to work at ECMWF, and so I still call this total column water vapor, which is the variable name in ERA 5. But it's precipitable water, PWV, which Dave was showing. It's the same variable. It's just the integrated mass of water in the column, okay? So sometimes he used units of millimeters. Here I've got kilograms per meter squared, which of course is exactly the same. So we can see that in this model simulation, when the convection is random, these are random states. Because we have lots of moisture sources, everywhere in the domain it stays moist, and so the mean is much higher. When we have clustered states, we have areas of the box which become very dry, so the mean is much drier, and we have more outgoing long-wave radiation. Remember that plot where we saw the dry areas in the tropics were where we had more outgoing long-wave radiation. So we really want to understand clustering, because it could be that if the way convection organizes changes as climates change, it could act as a positive or a negative feedback, depending if the clustering increases or the clustering decreases as climate changes. And first instances with very complicated models really don't show a lot of agreement between them in terms of this sensitivity. Some models go one way, some models go the other. Okay. Very briefly, so this is just to show the OLR basically increasing as we go from a random to an aggregated state, which has an impact of around 20 watts per meter squared in this particular model. What's driving organization in these? I'm going to go over this quite fast so that I get time to show some idealized stochastic model results. Okay. Well, even way back, so this was actually my PhD work back in '98. Okay. And actually, it's a bit of a pity that our PhDs are only 3 years in the UK, because I wish if we'd had a US-style PhD and I could have continued, I could have drilled down much more into this actually at the time. But basically, these models we're looking from above, we're just looking at structures in the boundary layer. When we had interactive radiation and surface fluxes, we can see these very strong bands of organized convection. And then what I did, starting from this organized state in this model, I homogenized surface fluxes, or I homogenized radiative heating. So basically, the radiation no longer saw this is cloudy, this is clear. It just basically got a kind of a mean profile, okay? And we can see that the organization starts to break out with surface flux homogenization, but much more strongly when we homogenize radiation already. But that's pretty much all we did there. We didn't go down into more details. And so this was kind of, you know, the topic wasn't studied that much. Chris Breverton then had a very nice paper in 2005, about 7 years after this. And then the field really started to take off. And one of the kind of people that's really central to the research in this is Alison Wing. And she's had a series of very, very nice papers looking at aggregation. And this was some of the earlier work where she was just looking at the budgets. And so this is an example where what she did is she organized all of the columns in the domain from driest to moistest. So this is basically taken that three-dimensional domain. You can imagine if each of these seats is a grid box, we just find the driest, that seat there, and we put it on the left. And we take the next driest and we put it next. And so we just go around each of the locations and we order them. And then she just basically looked at, for example, first of all, surface fluxes, sensible and latent? Are the radiative fluxes acting to increase the moist static energy in the areas where it's highest and decrease it where it's lowest? In other words, do they increase the variance and acting to organize and aggregate, or are they acting against the variance? So if this seat, which is driest, if a diabatic process where it's the lowest moist static energy is trying to increase it, then it's going to reduce the variance. It's acting against the gradients. Okay. So the red is where a process is acting to organize. And so in the early days of this simulation, she found the strongest was actually the long wave cloud radiation feedback, which was acting to strongly aggregate. So basically where we had warming, where we have clouds in the atmosphere, and we have more cooling in the dry areas, okay? And Young recently actually showed that it seemed to be that this was actually most important in then driving gradients in the boundary layer, okay? So I don't have time to talk about this too much, but this is an interesting paper to look at, Yang 2018, which I think was in JAS. Okay. Water vapor feedback, just showing this in a cartoon, but basically, as I said, convection moistens, but then that moist environment is also conducive to future convection. So we can imagine a two-way feedback. Grabowski and Moncrief in their paper showed that if they relaxed QV, the water vapor back to the horizontal mean, they broke up the clustering, for example, in their simulations. And I had a paper in 2001, which also looked at this water vapor feedback. Is this an example of kind of schooling? No, fish clump together for mutual protection. So maybe this is an example of a schooling feedback. Okay, and I've already mentioned radiative feedback. I'm going to skip over that in the interest of time. And then we can imagine surface flux feedback. So on Friday, we had a one-day symposium in Acapulco, which was focusing on cyclones. And of course, this kind of feedback in terms of convection enhancing winds is very important in tropical cyclones, but can also more generally have a role in aggregation. So enhanced surface fluxes in the neighborhood of convection can then basically increase the boundary layer moist static energy and again, make it more conducive to future convection. So that's in cyclones, that's referred to as the wishy feedback, okay? A couple of slides on why, again, we said, I said about the drying, but there's also a recent, well, this was actually now published in 2020. Time flies quickly now. We keep saying recent, and then suddenly you realize a paper is already like 15 years old or 20 years old. But basically, this is work I was also involved with. I was lucky enough to spend a couple of months visiting Sandrine in, I think it was 2018, 2019. And we worked together, along with Kerry was visiting as well, although we didn't overlap on this paper, where we looked at organization from using OLR. And so part of the difficulty there was to try and pick out where the updrafts of convection were from their overshooting tops. So that's what I was kind of involved in. And then basically, we tried to then assess the organization. And so we did that using this parameter called IORG, okay? So very briefly, in a nutshell, and I think I have a cartoon here, what IORG does is it simply looks at nearest neighbor distances. So again, imagine for a moment that you are all convective clouds, okay? So you're all convective clouds with your little anvils, okay? And now if you look around and you look at the person who's sitting next to you or nearest to you, okay, and look at that distance, okay? So if imagine all of you measure the distance to the nearest person, okay? So in some cases, you're sitting next to someone, it's a very small distance. Some people are sitting with some empty seats around you, so they have a bigger distance. Now, we can actually, if we assume that all of you just sat down randomly, there's a very simple theory that describes what the distribution of those distances should look like, okay? So if we accumulate those distances, it's just a viable distribution. So all IGORG does is simply compare the distances that we measure to the distribution that we would expect from a random distribution. If on average, at any given radius, there are more neighbors near you, or the distances are actually shorter, I should say, then we know that we have a clustered state. So the nice thing about this approach is it gives us a null hypothesis that we can compare to. So rather than just being a relative metric like variance of water vapor, it actually gives us a null model that we can compare to, which is randomness. And we can say, are we more clustered or less clustered than a random situation, okay? It's not the only index to do this, and it has advantages and disadvantages. And in fact, if you're interested in indexes of organization, Giovanni, who was working with me for his PhD and a short postdoc, who was on the co-author list, I forgot to mention my co-authors at the beginning on the first slide. He has a very nice paper that he put together in JAS with a big review of indices and actually suggesting a new one on indices that are being applied both to observations and also to simulations. Okay, so this IORG, if it's 0.5, we have randomness, and then if we have a value above 0.5, we have clustering. So when Adisu tried to apply this metric to these observations, you can see in both cases we have a clustered state, but there's a difference between this objective metric, okay? So if you were to glance at this picture, it's very difficult with our kind of human brains to kind of look at differences in organization here, because we tend to kind of zoom out at the biggest scales and so on. Whereas this metric, because it's nearest neighbors, is actually sensitive to the mesoscale organization because it's looking at the nearest distances, okay? So it's not very good at, it doesn't really see if you have a cluster of different convection elements and another cluster here, it doesn't look at the intercluster scale. Okay. So basically, he looked together with Sunscreen at the changes in this clustering metric over time for the whole of the tropics, okay? And they also looked at another, should we say, index, which is important for shallow clouds, and that's the inversion strength. So we can imagine that because the inversion strength might be important for low clouds, this is going to be important for the shortwave radiative budget because the low clouds impact the reflection of shortwave radiation because they've got warm cloud tops. They're not that important for the long wave top of atmosphere budget. Instead, this clustering metric is really looking at the locations of deep convection. So we expect that to be important for the long wave budget, okay? And so what we found with that is if we just took a very simple linear regression, okay, of basically the IORG organization index and the stability parameter, we could actually reproduce the year-to-year variability at the net radiative top of atmosphere budget, okay, very, very nicely. And both of these indices were important for this because, as I said, one's dominating the short wave changes and one the long wave, okay. And so we looked at the radiative kernels in this, and basically we could see that the most important kind of contribution of IORG was to the dryness of the descending branches, those radiative fins, which were associated with this organization. So it seemed to be showing that when we had more clustering, okay, we're basically having drier fins because we have like the convection sources all put together, okay. But as I mentioned, if we look at the nearest neighbor distances, you know, IORG is really just measuring convection organization on the mesoscale. So it really is, it's saying that these large scale radiative budgets, to some extent, are being controlled by what's going on the mesoscale in the tropics in terms of convection organization. And we actually have an analytical derivation of the IORG scaling inside that paper, okay? So in the interest of time, I should move on. And I'm going to step back now to these idealized simulations. Now, and I kind of already mentioned in passing that when we want to look at the climate sensitivity of organization as a function of sea surface temperature, okay, when we look in the RCEMIP, which is a big intercomparison study of many different cloud resolving models, they all do different things. And in fact, there are a lot of sensitivities in these experiments which are a little bit disturbing. So one of them is that the organization in this aggregation is basically sensitive to the domain size, is sensitive to the model resolution that you use, and it's also very sensitive to the physics that you use in these models. So even though they're cloud resolving, as I mentioned, they still rely on turbulence parameterizations and microphysics and so on. So this again is a result from Caroline Müller and Isaac Held. Each of these crosses or dots is one simulation of on the order of 50, 60 days going to equilibrium. Some of them cluster and some of them just stay random, okay? And we can see that both the domain size and also the resolution impacts whether we go to a clustered state or whether the convection stays random. At finer resolutions, we don't cluster. At smaller domains, we don't cluster, okay? And in the paper with Adisu, we also found when we were using WRF, almost a shocking resolution, physics dependency on the subgrid scale turbulence, okay? So if we take, these are basically 3D Smagorinsky approach to representing turbulence. I'm not going to tell you what that means, but you can talk to me in the coffee break if you want to know more details, okay? And one with a vertical PBL scheme and one without. These strongly clustered. But if we just use the out-of-the-box turbulence kinetic energy, this is a 1.5 order scheme, okay, or the 2D Smagorinsky, the convection just stays random, okay? So there is, when we look at this literature, if some of you get more interested, you'll see with the RCMIP, a lot of the models aggregate, but I've got a feeling it's a little bit of, how do you say this, positive, response in terms of, yeah, like you want to contribute to an experiment on aggregation. And so if your model doesn't aggregate, you try and play with it until it does, because it doesn't look much fun. It's a little bit like with climate sensitivity, although I'm on YouTube, so I have to be a little bit careful. No, you know, a couple of things have happened during my career that's made me strongly believe that people seem to tune away their models' results if they find that they are lying way outside what the last CMIP round would give. You know, if their model's giving a 8K climate sensitivity, they go, oh, back to the drawing board, and they turn their knobs until they get back inside, which I think is part of the reason why all the CMIP rounds pretty much have the same sensitivity over each round, okay? I mean, when Odysseus started his PhD, he was saying, oh, the model doesn't cluster. You know, I don't know what I'm doing wrong. And so this was really a big shock that, and also it's a shock, the fact that if you diagnose the mixing, there's an order of magnitude difference between the schemes in WAF in terms of the diagnosed mixing between updrafts and their environment. You remember that turbulence in the picture of that airplane? Okay, the way these models diagnose that turbulence has an order of magnitude difference between the schemes available in the operational WAF, in the WAF model. The operational model, by the way, is this one here, because it's faster. You can have longer time steps. So in the last part of this talk, I think I've got about 15 minutes if I leave time for questions. I wanted to just show some work also from the PhD of Giovanni, which was published just over a year ago in James. And what we tried to do is take a step back. We said, okay, we have this, you know, very strong physics sensitivity in these cloud resolving models. Can we take a step back and try and develop an even simpler idealized model to try and understand some of these sensitivities to domain size, resolution, and so on, okay? And so this model is simply one ordinary differential equation, okay? And I should have changed the math. I've got a partial, but this is should be an ordinary differential equation, okay? And it's just basically got three terms, okay? And what it tries to do is represent this feedback between convection and water vapor, but in a way, this feedback can be a proxy for all of these diabatic feedbacks that drive aggregation. So for example, the cloud radiate effects and so on, which is kind of wrapped up in this parameter. So what does this do? What we wanted to do is we set up this idealized model. We actually integrate this equation on a mesh of grid points, just like the cloud resolving model, okay? So again, imagine this room to be 200 by 200 kilometers. It's not exactly square, but you can use your imaginations, okay? It's also slightly sloped, but we will ignore that as well, okay? We split it up into grid boxes, which can be 1 kilometer or 2 kilometer wide, okay? And in each of these, we integrate this equation. And it's just one equation for the column water. So we had it TCWV before, total column water vapor. We had PWV before, and now I've just called it R, okay? And the reason why I'm calling it R is because I'm actually normalizing by the saturation value. I think Dave also introduced that as well. So it's basically, I think you called it the saturation ratio, no? Okay. So this is just basically a number that goes between 0, 1. It can even be more than 1 because this is actually the total column water divided by the saturation value. So if you have cloud in your column, it can be 1.03 or so. The first term basically says, this is the interesting term. This basically says each time step, we're going to choose a cell or some cells to be convective, okay? And I'm going to tell you how we do that in a moment. But it's a stochastic process, okay? If I'm chosen, so if where Spencer's sitting is chosen as a convective cell, he rapidly moistens his cell, okay? I'm not going to tell you how you do that, Spencer. Okay. I'll leave that to your imagination. I think there's a flask of water on the floor there. If you want, you can use that, okay? But you rapidly basically bring your location to saturation at this time scale, tau C, okay? Now, that water there in that cell, although we're integrating this at a short time step, and we made sure that we absolutely didn't have any time step sensitivity or so, Giovanni is extremely pedantic. So the numerical way we implemented this is absolutely bomb-proof, okay? And basically, if we choose a cell, it has an average lifetime of half an hour. It can be 20, it can be 40 minutes. It's a stochastic process. So it carries on keeping this location moist, okay? Now, that moisture doesn't just sit there. It diffuses out. So this is extremely simple. We're not representing the actual advection of moisture. We just mimic that by diffusion over time, which is this term here. So this K is the diffusivity, which represents how fast this moisture can mix. So what would be a parameter that would influence K? In which situation would K be much larger? If you think about, we talked about in the convection lectures, K could be smaller, it could be larger. What would impact K? For example, if we had wind shear, no? So in high shear environments, we might expect a much larger variance of K because we're more efficient. If I make a halo of water, shear would more efficiently spread that water vapor out over a larger area, okay? Just as one example, okay? And then last and not least, though, we have another term on the right, which is just that compensating substance, which we very simply represent as a relaxation over a much longer timescale, okay? On the order of 15 to 20 days back towards zero. So water is basically in a convective location, it spreads out by diffusion, and then we have substance drying, okay? Okay, so the interesting thing here is how do we choose this? Now we could just make this random, okay, so that we have a set convective fraction, which is anyway can be constant time. We could also have a diurnal cycle. And if we just have this random, then what do we expect? We expect the convection just to be random and continue to be random because diffusion reduces the horizontal variance, obviously, because if we diffuse, it's like mixing up with a spoon. What does this term do to the horizontal variance? Everything is going back towards zero. If we wait long enough, we only had that. Eventually, we have zero everywhere. So we're reducing variance. So the only way we can increase the variance is through this term. So what we could do, instead of having this random, we can make this sensitive to water vapor so that we're more likely to choose a grid box if it's already moister compared to a dry box. So let's see what happens. This is just a cartoon, basically, of this simulation. Now, we actually simulate this in 3 dimensions, but Giovanni made this kind of transect just to kind of illustrate what's going on, no? To give you an idea. We choose these random cells, they're moistening the environment, and over time you can see this moisture diffusing out, but also compared to the initial conditions, you can see the slow substance drying over time, okay? Now, of course, we actually simulate this in 3 dimensions and not 2. Let me go on. So what happens in 3 dimensions? Well, it's kind of interesting. The only difference between these simulations is the convective fraction that we actually simulate and specify. So here, I think this is in the order of 1%, and this is in the order of 0.5%, okay? So, of course, the convective fraction in reality depends on where you are embedded in this kind of large-scale overturning circulation. If you're in the, right in the warm pole, in the upward branches of the Hadley and Walker circulations, you expect a higher density of convection. So what you see is when we have a higher density, more moisture sources locally, it doesn't aggregate. Everything stays random. The colors of the humidity, and we're moist everywhere, okay? Instead, in this situation where we have a slightly lower number of convective sources, what happens is we get a banding structure and slowly we kind of collapse down then to a single location, which looks like the cloud resolving model simulation I showed you earlier, okay? So this is just showing the column humidity. So the model is bistable. It can simulate random states and it can simulate clustered states, okay? Now, what we find is the model also reproduces the bulk sensitivities we see in the cloud resolving models. So if I have a small domain on the left, it stays random, just like in Caroline simulations. But if we go to larger domains, then we have clustering with exactly the same setup, okay? So we have the sensitivity to domain size that we see in Caroline's cloud resolving model runs, okay? So why is this, do we think? Well, what we thought was basically is what's going to be key is in the random state, what is the largest expected convective free area, okay? Let's imagine we have a domain and we have a collection of points and I just throw them on the page, just throw them up in the air and they land down randomly, okay? We can derive from theory what we expect the mean. If we could do this 1,000 times, okay? Each time it's going to be different, but from theory we can predict what is the largest free area that we expect. So if we look at the seats now, we have an area of seats in the middle there, which is the biggest area of free patch without convection, because you're all still convection, by the way, don't forget that, okay? So that's the largest area. So we can derive that from theory, what that largest free area is. Now, the bigger this area is, the drier the anomalies are expected to be in the random state. Now, remember that I is sensitive to the water vapor. We take it from Chris Brereton's relationship. And so the bigger the perturbations, the more chance they can be acted upon on the I function, which is sensitive to the water vapor. So we have less chance of choosing this for convection and more chance over here, okay? So this is our theory compared to observations, and you can see that the theory lies exactly on terms of this observations, where we just run thousands and thousands of just random simulations of just throwing points on a page and looking at the patch. And that just shows you that our theory works perfectly in terms of predicting this convective-free patch. In the same way, we can look at the resolution sensitivity. Here we have 4 simulations which use 4, 2, 1, and half a kilometer. And the model tips over almost at roughly the same resolution that we get from the cloud resolver models, okay? So if we have a fine resolution, it's not organizing. And if we have a coarse resolution, it is, okay? Now, again, why is this happening? Also, interestingly, we can also get band organization structures that you sometimes see in the cloud resolving models. Again, this comes back to the location of your nearest convective neighbor. The model does not constrain the number of points, it constrains the convective fraction. So if we go down from, say, a 1 kilometer to a half a kilometer resolution, in the 1 kilometer, we have 1 convective cell that in the half kilometer is now split up into 4 separate cells, okay? Now, you might say, well, actually, that doesn't seem like, too great an assumption, but the thing is that in the cloud resolving models, and this is an example, there are 2 papers here that for reference. If we actually look at for example, the updraft width as a function of the resolution in the cloud resolving models, it hasn't saturated. It hasn't come to basically, how do you say, when you, I'm trying to look for the word, when you reach, when you asymptote, you find that even increasing resolution no longer changes the updraft size. Yeah, converged, that's the word I was looking for, sorry. So it hasn't converged. So the models are actually doing this kind of thing. When you go to finer resolutions, they have many more convective cells, okay? Of course, in our model, this is extreme because we really have no convergence of these cells at all. So this is probably exaggerating slightly this, okay? Also, the physics is very dependent. If we have a higher diffusion, then we find that we basically stay as you expect. Higher diffusion, we spread out humidity more effectively and we stay random. Instead, if we have a lower diffusion, we become clustered. Okay, so we can see we can have both aggregated and random events, random states, simply by changing the substance rates, changing the diffusion, or changing the sensitivity of convection to moisture, okay? Interestingly, this red line, the blue line here is the default setup where we try to get the parameters to fit what we expect from observations the best. This blue line is using Chris Breverton's fit from the earlier version of TRIM out of the box. And the red line is using the later paper from, I think it was Russell in 2017, which was to revise it with TRIM version 7. So this is TRIM version 6, and this is TRIM version 7. And just by chance, we haven't fixed anything. It was quite remarkable that it actually tipped us over from one state to another using these 2 different resolutions, okay? So what we wanted to do is try and put together all of this together into one dimensionless parameter to try and predict when we would get aggregation, okay? So for example, we can take 2 parameters of this model, K and tau sub, and we can put them together and they have units of meters squared, okay? So that's an area. So this is basically an area of influence of the humidity halo. If we have a higher K, it means that we spread out vapor more effectively, but if we have higher substance, it dries more quickly and that prevents the halo basically from being effectively so large. It makes it steeper, okay? So K tau sub is an area of influence, okay? So we said, okay, is the aggregation, related to that? That was our first step. And in fact, it was. If we look at basically lots and lots of simulations. So here, you can't see it, we've just done contours, but basically we're looking at contours of the final state variance humidity, okay? So if we have basically here much higher values than we have here, it basically means we have clustered convection, and here we have random convection. So each of these points is basically, in this diagram, is an experiment, because this model is very cheap, with 1 value of tau and 1 value of K. Okay, and what you see is this band of contours here, which shows a transition. So you can see a transition from basically random to clustered along this line, and it lies exactly in parallel with an isopleph of k tau, okay, which is the radius of influence of convection. So then we wanted to take a step further, and we wanted to try and put it together in a dimension as constant, okay? Now, I don't have time now because to go into the details of the derivation, but this basically puts together this prediction of the biggest free patch together with this area of influence into one parameter here. And this AD is the strength of the water vapor feedback into one dimensionless constant, which we called NAG, the aggregation constant, okay? So then we wanted to test this. This incorporates the domain size. This D here, which is this dry patch, also is a function of the resolution of the simulation. We popped this all together, and then we tested it, running basically thousands of simulations. So each dot is a simulation with this stochastic model, using different domain sizes, using different resolutions, and using different physics parameter values of both the diffusion and the substance and so on. And then what we find is on the x-axis is this parameter, and as we hoped, we find that we have basically a switch in the regimes between clustered and random convection, okay? So we believe that this basically explains this theory of why we get this sensitivity in these cloud resolving models and also the physics. In fact, in view of this, I completely reinterpreted the results from the early cloud resolving models in terms of the subgrid scale diffusion. I thought it was due to the mixing and the updrafts and actually an entrainment sensitivity. But now, looking back at those experiments, it turns out that when you have very high mixing on the subgrid scale, you have much fatter updrafts, but then you have fewer to balance the radiated cooling. So you have fewer fatter updrafts, so you have bigger distances. And so we've actually found, we've got a paper in preparation now, also with a group from Padua, where we've actually tried to derive an approximation to this as best we can from the first 2 days of the simulations in RC MIP, and then to try and predict if each one of those models will eventually cluster, and it seems to work pretty well. So that's, it seems to be that we can actually use this to predict if we're going to have basically aggregation. So this is what I was just saying here. I'm talking ahead of my slides. So in conclusion, convection self-aggregation is driven by predominantly cloud-radiated feedbacks, and to a certain extent there's a secondary role for surface flux feedback. So we can see the existence of this bistable state where we can have aggregation or random convection, okay? Future changes in this organization seem to be very model dependent. When you change the bottom boundary condition temperature, the way the aggregation changes is very different between models and also between the way you measure that aggregation. So I didn't get a chance to talk about that in more detail. It's dependent, the aggregation, on resolution, domain size, and it's physics dependent. And I think that we've made good progress, Giovanni and I, with this simple stochastic model to at least explain some of these sensitivities. And at the end, I said, can we predict observations and realistic full physics models on NAG? And as I was saying, I didn't show results today, but the work we've been doing together with the group in Padua seems to show that, in fact, there's good hope that we can actually apply this at least to numerical models. Okay. Last but not least, I think Simona might advertise this as well. We've actually had quite a big grant actually awarded from the Wellcome Trust, which is actually on climate and health. It's going to start this summer in 2025. So ICDP is leading that. We've got partners across basically Senegal, Ethiopia, Kenya, USA, and Switzerland. Quite a few of us are going to be hiring postdocs. And so particularly one of the positions in ICDP and the 2 positions with Simona in Trento, although this is on climate impacts on health in Africa, those positions are very much focused on monsoon variability and future changes in monsoons and so on. So they're much more on the climate and monsoon aspects, okay, inside a project which has a health aspect. So if anybody's interested, or you know people in other institutes or organizations that might be interested, please get in touch. We'll be opening these positions quite soon, as soon as we get the grant agreement signed. Thank you.
Time for a couple questions, I guess. I guess the first thing we'll do is we'll run out and do the photo when we're done, and then we'll do the coffee and stuff. Yeah. Okay. So, questions? Yep. Okay.
Really nice, Alex. Thank you. I think I will have like question for in converting that with the ITC on like Earth models. Do you believe that there is like a based on your stochastic results? Do you think that like convection permitting but not going that deep into cloud resolving are better for simulating the ITCC on like not on like a climatological time scale, but like on the day-to-day time scale? Because we know that in observation, the ITC is not like this continuous band of precipitation. Instead, these random storms that with time they tend to cluster into these kind of bands of precipitation. So do you think that based on that, not going that deep into high resolution is better for getting these clusters?
Okay, so I think, I mean, this is going to be the topic of one of Simona's 2 talks in the afternoon. So she'll be talking more about this, particularly in the context of a recent project called NextGems, which is coming to a close now, and was running 2 models, ICON and the IFS, at kind of K-scale, kind of near, near convective permitting. So a lot of the simulations were at 5 or 10 kilometers. They show, and I think Simona, I don't want to kind of steal any of her results from the afternoon, but they will show that, it's definitely not a panacea out of the box. And I think that some of the expectation for the K-scale models was perhaps a little bit too high in the short term. We're not going to have the convection parameterization anymore. Everything's going to work fine. And of course, as we see very clearly from some of these results, and I really encourage you to look at the RC MIP papers as well from Allison and her co-authors. They show that, these simulations are vastly different in the way they represent aggregation and so on. And that's because, as Dave pointed out quite rightly, we still have, for example, sensitivity to a lot of the diabatic processes that represent visualizations. So one example was for the ICON model is the way that the latent heat fluxes were represented when they moved to K-scale. The low wind representation of those fluxes, didn't work that well. And that meant, for example, they had a very bad problem, which was partly due to that in terms of the split ITCC in the warm pool region. And Simona's going to be talking about that in much more detail. I don't want to kind of go into details of that. And again, I mentioned here subgrid scale mixing. So, it's hugely important. But at the same time, in the NextGems meetings, I don't think I've heard it talked about hardly at all. They just take the subgrid scale scheme out of the box, and it's not talked about that much. And part of the problem with these K-scale models is that they can only be run by the modeling centers because they're huge. So it means that, like, for example, it's quite frustrating sometimes when Simona and I were working on an investigation of these low winds. It'd be really nice to just be able to run a short run, and that's not very easy to do at the moment. I'm hoping maybe part of the thing if Eve goes ahead, which is an idea of having these global centers for K-scale modeling, that it will be much more democratic and open to be able to at least the community to run their short-term experiments. And I think that's going to be really important to do. So it's definitely not the panacea, but I think it's a little bit like when I was working at ECMWF. Every now and again, the computer would increase and they would increase the resolution. Often the skill score didn't go up, but they still did it because it gave the opportunity to get more out of the system. And I think there's a lot of potential moving to K-scale to actually represent these processes better. It's just that we need to do a lot of work before we get there.
Okay. Thanks.
Thanks, Adrian. Really, really cool, this model, this stochastic model. Just wanted to clarify, when you brought up the bistability at first, that slide, you were showing an aggregated and a non-aggregated state, but there was at least one parameter different between the two. But then later you were speaking about hysteresis, where for the exact same configuration, but different initial conditions, you get, and that's what I think of as bistability. Not to be pedantic, but just.
Yes, no, you're right. No, I was being a little bit sloppy in my kind of thing. It is actually a hysteresis. So even in the stochastic model, and this actually tends to be a bit stronger in the cloud resolver models. These states are a bit sticky, okay? And you can even see a hint of that if I go back to this thing here. No, part of this is there's stochasticity in these states. But if you take this stochastic model and you have a configuration that gives you random convection, and then you change the one that gives you, basically slowly you increase it. So you have a new state, and then you flip to basically something which is aggregated. If you then do the reverse and go the other way, it doesn't shift at exactly the same point. In this stochastic model, that hysteresis is quite weak. Okay, and even in the cloud resolver models, in fact, that is something that really depends on the model. So my PhD model, actually there, the LEM, that very quickly broke up the organization within 4 days. I can find the plot there. In these simulations here, 4 or 5 days, and it broke up the state. Whereas in some cloud resolver models, the states seem to be much more sticky. And so you really have to push it a lot more to go back into a random state. Once it's aggregated, it stays aggregated. This model, again, had quite a weak hysteresis, and it was quite easy to break up the organization. So it is a hysteresis. So what I should have said then, because I was kind of saying, I should have said that you have multiple equilibria. Okay, so you have multiple equilibria, but it also, there is a, like, bistability with a hysteresis, which I hadn't shown in the plot there. So you're right, I was being a little bit sloppy with my terminology.
Okay, all right, so let's see, what are we going to do, Alejandro?
So I know that some of you might be or are dying for a cup of coffee, myself included, but first we are going to have the workshop photo. It's going to be here outside, so we are going through this door, and here outside there is
Okay, all right, I guess we can start. So Jorge is going to talk to us with the about the variability of precipitation in the Grijalva sub-basins. Okay, if you don't know Jorge, he is the director of our institute. I guess by now you probably should know. Okay.
Okay. Well, thank you very much, Steve. I will try to relate this talk with the previous talks, which is at the first step looks not easy, but there are a lot of relations. So, okay. So I will talk about this. That it's going on and off, right? Right. Hello, hello, hello. That's it. Okay. I will talk about this. This area, which is the Grijalva Basin, and it's very interesting area because it has a lot of precipitation. In Mexico, I should put a map of the precipitation in Mexico, but we have this area is the area with more precipitation, in particular this southern part of the Gulf of Mexico, of course. And by the way, it's the Mexican monsoon. So there's also a confusion on that. You can see the old papers. Yeah. Anyway. And there's another branch of precipitation along the Pacific and along the Sierra Madre. But this area has a lot of precipitation, and it's a very interesting area with also the most hydrological energy production and the more floodings in the last decades. Here we see a focus on the area. The basin, this is the upper basin. There's also a lower basin in the north, in the state of Tabasco. But we divided this in sub-basins based on 4 big dams that are here. This is the largest dam in Mexico. Not working anymore. The Angostura Dam. Then the second one, the Chicoacén, Malpaso, and the last one is the Peñitas. So we call these sub-basins, are part of the large basin. Now this area is in the trade winds, as you can see, and we have been told that. So most of the winds are from the east. And if we look in this more high resolution map, we see that although there is also winds from the east, there are a lot of variability and the influence of the high and low pressure systems, mainly the high. The ITCC, this is for winter, but the ITCC also have an important migration. And I should say that here, the ITCC used to be southern than in the Pacific, which is also very important for the precipitation in Mexico, this different shift. And there's a lot of interannual variability on that. So that also should be taken into account. So what are the causes of precipitation on this area? Well, of course, it's on the trade winds. We have this advection of moisture. But there are also easterly waves that affect the area and produce precipitation. We have here about the easterly waves during this event. There are also tropical cyclones, both from the Atlantic and also from the eastern tropical Pacific. Both systems affect the area, not exactly in the sub-areas, not exactly in the same way, but both affect the area. And cold fronts, as the one that we have today, and we see here affecting. And they are very important in this area. Making a zoom on the surface winds from scatterometer. This is a paper from Rosario in 2000 et al. In 2007. And you can see here that the ITCC in particular has a very strong migration. The trades from the south even reverse and have an eastward component, in particular in June. and more in September, and also produces a lot of water vapor transport in addition to the tropical cyclones that affect the area. And there is a, between June and September, the wind gaps displaces the ITCC and reduces the precipitation. So some people make summer average and put all together, which is a mess. Don't do that. At least for Mexico, right? Because we have these systems that affect the area. The dams are very interesting because they are in series. We have the biggest dam, which is Angostura, with a very large capacity. Here are the capacities in millions of cubic meters. Then a very small one, Chicoacén. Then another large one, which is Malpaso, and there is a small one in Peñitas. To fill these big ones take months. To fill these ones take days. So to manage the system require a lot of skills. And that's the main goal of our concern. I have to say that in 2007, there were a very big flood, and then there were another one in 2020 that floods almost the entire plateau of Tabasco, near all the area around Villahermosa. You see here the precipitation, the flooding and precipitation in October, November 2007. So we have been very concerned on that and have a lot of students and papers related in some way of this system, how they affect the area. How much is this precipitation? There's a lot. Here the precipitation in the event of October 2007. We separate the event in two stages. The first stage give this precipitation. During almost 3 days, there were precipitations of more than 400 millimeters, more than 300 millimeters. And in the second event, another 3 days, 4 days, there were precipitations of more than 800 millimeters. See, if you remember the graphs of some of the graphs, say the ones from Dave, the precipitation water vertically integrated, it's around 50, 60 millimeters. So how can we get 800 millimeters in 3 days? So that's a very important question. And this is more than twice than the Spanish got this year, the last year. So we get these precipitations. Even in 1 day, we have measured 400 millimeters. So that's a very interesting issue. Of course, when this happens, the river go away. How do you say desbordar? It's go and overflow, and the entire area get flood. There's a very important issue and a very big change when the river goes out of their pathway than when not. So it seems that it happens because of the precipitation, but there is a very tipping point that make a very big difference. Oh, here you see these are measurements from stations. The first event from 23 or something 22 to 25, then no precipitation, then again the second event. And this was caused by a cold front passing through and in interaction with a tropical system. That's the worst combination that you can have. So we make a study on that with WRF. We make the validation. Here in dots, you see the precipitation measured by the stations, and in square lines, the one from WRF. So we use to understand what happened, and we make this transects. This work was done by a master student in 2009, I guess. And what we see, it's a very strong jet of water vapor. This the transect in the north, then the second, the third, and the fourth. And we see this very strong jet of water vapor. And as you can see here, we have this is a plateau with, I guess, less than 20 meters above mean sea level. But then here you have altitudes of more than 1,000 meters. So there is a very strong topographic forcing that produces the convection and the precipitation. So somehow we have the jet coming south, the interaction and precipitation, and that's going on and on and on. And this is worse when the system is stationary. The other day, one of the questions was, which are the hurricanes that produces more precipitation? And the answer is not the biggest one, it's the stationary ones. The stationary in front of the coast that produces continuously water vapor transport, and because of the topography of Mexico, you get the forcing, topographic forcing, and the continuous precipitation almost in the same areas. And this happens in both areas of in both oceans. So this cold front crosses here, and then it reverses. It came in a stationary front and stayed for several days, 3 days in the area. And this is from the second part of the event, I would say the path of the water vapor trap and the precipitation, and also the same pattern with a strong transport of in very, I would say, shallow part of the atmosphere, in the lower part of the troposphere, right? So that happens in 2007. Then in 2020, we have precipitations that were also very large. There were also fronts coming from the northern Gulf of Mexico and interacting with tropical cyclones, several of them. Remember, this tropical cyclone season was very active. We have Gamma, Kappa, Iota, and several tropical cyclones, even in November. And we have this precipitation. This is the date is here, 28. Then a period, 28 to 30. Then 1st of October to 31 of October. And if we integrate from 28th of September to 24 of November, we got precipitations of more than 2,000 millimeters. So that's huge precipitation. No? Remember, for example, the precipitation in Mexico City for the entire year is 800 millimeters. So we got in a few days much more than that. And what happened there? There was a cold front interacting with a tropical cyclone. In particular, this is Gamma, which were there stationary also. An evaluation of the flooding was made by one of our collaborators. And the idea was to identify the flooding area. Here you see the river going this way. The black areas are flooded areas. So it was quantified that. This is before the event and after the event with this difference of flooding. You see some areas that were previously flooded here in black, in the middle of the surrounded areas. But all this blue was flooded after the event, during the event. This for the period between October 4 and October 22. And also these areas were flooded. Also, you can see here and the difference. You can see here the difference. All these areas were flooded. Also, a different view. All these areas were before the event, and after the event were flooded. So there were a lot of contribution of local precipitation, but some from the river overflow. Now, let's see how is the precipitation there. There are some ideas that I want to share with you. These are the mean precipitation for each of the subbasins. And these are the mean for the period 1990 to 2020, 30 years of mean. And for many decisions, politics, they use the mean. And I have been trying to say, don't use just the mean. Even if you are going to use one number, use the median. Because when there are strong events, the mean shift to the high events. If you make decisions thinking that half of the years will have, I will say, more than the mean and half less than the mean, you will always have dryness. And that happens in Mexico because they use the means for taking decisions. They have to use the medians, in particular in Mexico, because the distribution has a lot of bias. So for the dams, we have been suggesting to try to implement a model with different colleagues and postdocs. And the idea is that the volume change, and we have to think on that, the volume change only depends on precipitation. Part of the precipitation is evaporated or infiltrated. Then the inflow from upstream, and then the outflow. That's the change in the volume of each of the basins. And we have to that in mind. And we can make, and also have to consider that it's a coupled system, and we have an equation for each of the dams. And we can have several restrictions. For example, we don't want that the outflow will more than some number, but we also don't want that the level of a dam will above some level, right? I'm not going to stop on that, but I have to comment that in the hydrology, they use the guide curves. The idea is what should be the level of a dam each period of the year. And that's the information that we have to deal with. A very simple one, you can think, what's the average outflow of a dam during the year? Then you put this number as a constant, and then you subtract the precipitation and get the curve, right? So, but that's not the only one restriction, so you can put more restrictions. Now, think on these 4 subbasins. I want to see these figures very carefully. This is for each one of the dams. And the numbers are the percentiles of the precipitation for each month during the year. I have to say that for Angostura and Malpaso, the time scale is of months. It's very important. Even you can go into 15 days. But you don't want to go into what is the precipitation in 1 day. That doesn't really hurt the dam, unless you are already in the limit. But for planification, you have to go into lower frequencies. And for the smallest one, you need to go into meteorological scale. So there you have to use days. So in particular, I think how this behaves is the 50% percentile show you a very clear midsummer drought, which is related with the system of winds that I show in the beginning. And 25 to 75 percentiles is the interquartile range, but you also have the maximum historically in red and the minimum in yellow. You have to think that this happens in 1 month of the entire period, but not the same year. So that also have to be taken into account. So with these figures, you can deal with what's the probability that I can have some precipitation in a specific year instead of just working with the mean. And one thing that it has to be noticed is that mainly we can say the precipitation season begins in May and ends in October, say for example, Angostura. But for Peñitas, the story is very different. Even for the 50% percentile, we still have precipitations in November, very important ones, and in December, and even extreme events in October, November, and December. And another thing that's very interesting to notice is that the precipitation here, the scale in millimeters per day, can reach 30 millimeters per day on average on a month. It's not a one-day precipitation, it's an entire month. While in Angostura, it's around 17, 18 millimeters per day. And on average, we'll talk about 10 millimeters per day, while here we talk about 15 millimeters per day. So there's more precipitation in the subbasin of Peñitas. One interesting thing is the year 2020, which is shown here in purple, to identify where the precipitation was large and where affected more. All the basins were affected in an event by the end of May and June, which is here in purple. In particular here, you can see in Chicoacén, here in Malpaso, and in Peñitas. This is related with the tropical cyclones Amanda and Cristobal. It was a very interesting system that comes from the Pacific, go through Guatemala, get into Campeche, then went into the Gulf of Mexico, turn around, go south, and then crosses the entire Yucatan Peninsula, flooding the entire Yucatan Peninsula. In the Yucatan Peninsula, there are no rivers, so the flooding comes from the ground upwards. So there were no way to remove the water except for waiting. Then a second event was related with the interaction of fronts with the tropical cyclones, and that began in September, October, and then reached the historical record of the analyzed period, getting into more than 4,000 millimeters in the year. One thing is interesting is that this affects the basin of Peñitas, but not the subbasin of Angostura. So there is a big difference, even they are close areas. So also have to take that into account. And we see the daily averages, which may take some time to notice, but this you can identify the events, and some events were also recorded, were here. And on average, we get even 200 millimeters. But you have to think that we are not presenting, I didn't say it on detail, but we are not looking one station. We are looking the average of a sub-basin, which is much more than the precipitation that one station can get. And here we got a running mean average of 30 days. And we see the events, very strong events here, Amanda and Cristobal. And then the second events associated with the interaction of tropical cyclones and fronts. What happened? The fronts helps to transport, to condense the water vapor in the tropical systems, and then both systems, when they interact, sometimes they transport continuously the water vapor into the continent. Now we see, as everybody can note, want to know, the influence of the El Niño And for the rainy season, what is noticed here in blue, that during La Nina years, the precipitation, for example, in Angostura is close to the 75 percentile, while during El Nino years is close to the 25 percentile. And that is more or less true for all the subbasins, so there's more precipitation during La Nina years than during El Nino years in this area. In the case of Peñitas, it's, I don't have the details here, but it's more interesting because if there is a tropical cyclone, there is a peak. There is not a tropical cyclone, there's not above average. So it's more randomly. So we identify the number of tropical cyclones. We are presenting here just the trajectories during neutral, El Nino, and La Nina. And you can see that there are more events, particularly from the Caribbean and the Gulf of Mexico during La Nina years as one of the causes that increases the precipitation. Now, there is not also El Nino. It's also very important. Here in Mexico, people always say El Nino, El Nino, El Nino, which is very, very important. I'm not saying it's not important. But in a study that was done by Straffon and collaborators, Alejandra divided the precipitation season in 3 stages, taking the midsummer drought as a criteria. So during the midsummer drought, before and after, and she uses the same area that Rosario uses before, which is this area, precipitation. And for this area, she analyzes. One thing is that there is no correlation, or there is a low correlation between the anomaly of precipitation between stages, which also suggests not to put it all together. So, because you can have a, we'll say, May, June, very rainy period, but then during September, October, the opposite. Or so for one of the results that are very important is that for the midsummer period and for the first period, for example, these are the 6 years analyzed. She analyzed like 40 years, but the 6 years with more precipitation in the box here, the SST anomaly. So they were very warm Atlantic tropical ocean. And the opposite, the dry years were associated with cold sea surface temperature in the Atlantic. So the SST is important. So it's okay. And that changes for the third period. For the third period, or the third stage, the Pacific became more important, in particular the equatorial Pacific and El Nino area. Trends. Well, it doesn't look like there is an homogeneous trend. Positive in Angostura and Peñitas, and negative in Chicoacén and Malpaso. There's also things that have to be studied with more details in this case, because the stations were not the same for the entire period. So had to be done some more work. It cannot be concluded something from here, I guess. But we show here. In summary, well, I will say that the precipitation in the Peñita subbasin follows a different pattern than the other subbasins, and it's higher than in the other 3 dams. In Peñita's subbasins during autumn, there can be also a lot of precipitation. That's very important for the planification of the operation of the dams. In the case of the flooding of 2020, the area of Malpaso and Peñitas were the ones that were really on the highest years, and in particular, Peñitas was the record precipitation in the analyzed period. I said that during La Niña years, precipitation is higher, and for the trends, we cannot conclude something, right? I will say that. Thank you.
Okay, we have time for many questions.
I guess.
We go to participants first in general.
Thank you very much for the presentation. I was thinking, because it's true, we are using normally La Niña or El Niño in order to understand what's going to happen for forecast in the Grijalva River. But I was wondering if there is other oscillation or other parameter which we can use in order to understand what is going to happen in those sub-basin that, as you said, Peñitas is the more complicated, and socially and because of the location, it's also important for our country.
Okay. Yes, well, I also show that the Atlantic is tropical Atlantic temperature anomalies is very important. In the paper from Alejandra, he analyzed several variables like zonal winds, meridional winds, sea level pressure. So there are more, no? For example, sea level pressure also correlates very high, although the timescales are shorter. But of course, during low pressure in the area, in the sense of an average of relatively several weeks, you see more precipitation, right? And so yes, ENSO is a factor. I will say the Atlantic, it's very important, in particular in the first part of the precipitation season. In Alejandra division, the first two stages, I would say May, June, and then July, August. Although the precipitation reduces during the midsummer drought, there are years where you have precipitation above that mean or below that mean, right? And I think Rosario and her students do some research on other oscillations, but I don't remember exactly the results they got. So they combine El Nino with other oscillations, right? You cannot.
Yes, it's very quickly. Another thing is I realized that for neutral conditions, it is more likely to have very good precipitations in the sub-basin, neutral conditions. Oh, I think that's the results that we are trying to understand from the analysis, than in neutral conditions from the phenomenon the ENSO.
It's close to the mean.
It's close to the mean. Okay,
Yes.
thank you.
It is between El Niño and La Niña.
I think I have just like a quick question for the Peñitas sub-basin. That's the one that is most affected by tropical cyclone, right?
And by fronts, I will say. And the point is, I want to say is that fronts itself do not bring too much precipitation. It's fronts interacting with tropical systems. And in particular, fronts, stationary fronts.
Yeah, I think my question related to that, and I believe because Christian she has some the data from precipitation only coming from tropical cyclones, right? And what I see is that the trend is for at least for that sub-basin is a little bit different from the trend that we observe for ENSO, for example. I know that in observation we have an El Nino-like trend which will suppress TC activity on the Atlantic side. So I was just curious, like, if that will be like a direct effect from TCs or something like that. Yeah.
What was the question? Sorry.
Yeah. So no, my question was that if this basin was affected more, like more than the other basins that are close by for this, and but the trend look a little bit different of the TC activity. So if you have an input on that.
And I have to check that, but yeah, I have to say that the ITCC moves northward during La Nina years, right? That's very clear in the Pacific, but also I just mentioned, but the relative position of the ITCC in the Atlantic and in the Pacific, which people have not put too much attention, they have a variability, interannual variability, and make a lot of difference in the precipitation in this area.
Thanks.
Of the differences that stand out in the Peñita subbasin, one of them appeared to be that it doesn't have a clear midsummer route. You could comment on that.
Yeah, well, they have a relative maximum in June, then reduces in July. But the point is that the second part of the precipitation season make a very big difference with a strong peak. This is the mean. Yeah, the mean is the green. Very strong peak in September. So, it's not like Angostura is very symmetric, but there is a midsummer signal in Peñita.
Thank you.
Questions?
Hi, Jorge. I have a question. Oh, sorry. Students first. Oh, I was just wondering, Jorge, if you know, from the event of the 2020, if this also created like a big spike in health problems in that area. Do you know from historical records, it represents a very bad year also for that people?
Well, it was very, very complicated. You can, I don't have the numbers right now, but I used to have them. The affected people in the affected area is gigantic, but the response of the government was very, very strong. Meaning, from the beginning, there were a lot of response for example, dengue. They were very concerned for water quality, for drinking. There were concerns of pollution because once there is a flooding, there could be pollutants. And I'm not aware of big health problems, but I'm aware that there was a very big response. I was there for several days. Even I was in the chopper, checking all I have a lot of photos from the chopper. The flooded areas, it's just amazing. You see areas, it's like lagoons, bigger lagoons, and everything was flooded. So, and I guess there was a lot of, I would say, evacuation of people from the area. But I cannot say for sure that there were not health problems. You can expect it. One thing is there were no casualties. This is interesting. No casualties. And we have a very strong discussion because I was saying Tabasco will be flooded, and Comisión Federal de Electricidad says no, we have everything on control. And so there were days and days of big discussions at all levels. And the governor of Tabasco was very concerned about the flooding before it happens. So they were making a lot of decisions, which was very different than in 2007. In 2007, they first flood and then they evacuate. Here they first evacuate and then they flood. Because you know there will going to be a flooding because it depends a lot on the dam operation. And it takes like 7 or 8 hours from the water from the Peñitas Dam into the more populated area, Villahermosa and surrounded areas to be reached. So there were a lot of, I would say, actions to prevent bigger damage to the population.
Thank you very much for your presentation. Two questions I've got. The first one, the upper basin of the Grijalva River is well monitored and controlled, but I also read that in both events, the uncontrolled rivers downstream, for example, the La Sierra rivers and everything, have big contributions towards flooding. So I don't know, in your experience, if the atmospheric results over the area is like well monitored, or is it like not so relevant, or I don't know, what is your insights on the
I
downstream
didn't
rivers?
mention, it's a very good point. I will say, I don't know if I have maybe here. Yeah, this is the Grijalva basin. This is the limits with Guatemala. So this part of the basin belongs to Guatemala. And here is the Usumacinta River. And as you said, I'm sorry, these are the contributions from the Usumacinta, and these three are called the Ríos de la Sierra, and these are not controlled by dams. And certainly, they have a very big contribution, and they join together in the southeast part of Villahermosa, in this area. And there is always people saying, no, the flooding comes from the La Sierra. And I think it's something not very well solved to really make the separation and the attribution of the contribution to each one. But there is a lot of data because these are controlled by the river level, but there are measurements of the flux to calibrate the level of the rivers in some points. Of course, the calibration is for each point. And the local people say, I know the water comes from Grijalva or from La Sierra because of the color of the water. So that's a very interesting discussion. So, yeah.
And the second one, it's very simple. When you were comparing the events from 2007 to 2020, I think that in 2007, the Macayo was still not, I don't know if construct or in operation. And for the 2020, it was already built, but the results from the events were still flooding, was important floodings. So are the events in the 2020 scenario were stronger, that it caused the same situation, or what would happen then?
Well, that's also very different, very difficult question. In 2007, the city of Villahermosa got flooded. In 2020, almost none. And because of two reasons, the Macayo and because of the water were, let's say, derived to other areas. So there are a lot of infrastructures that allows to control where the water is going to flood. So they were very, very careful to not flood Villahermosa in 2020, but not in 2007. And after the flooding of 2007, they built a lot of infrastructure infrastructures. The one that you mentioned in Macayo and other ones. Yeah. So currently it's very complicated. There's a lot of how do you say compuertas? Eh? A lot of gates, they open and close, and ways to manage the water. Yeah.
Thank you.
But here the idea is to try to do something before the water reaches the the low basin. At least get less water going to that area. Okay. Thank you.
Necesito permiso de share screen. Gracias. Gracias. Okay. Buenas tardes. Sí, pues quiero que hablar un poco del español. Yo tenía las clases del español cuando en la escuela primaria y secundaria de 4 y 5 años y por eso yo sé un poco o pues un poquito. Ah, pero quiero que decir muchas gracias a toda la gente aquí. Esta es mi primera vez en UNAM y mi primera vez en Ciudad de México. Y los dos son qué bonita, qué fantástica. Y la gente también. Y por eso, sí, muchas gracias. Simona, Adrian, I said that Adrian and Simona are great. And yeah. Okay, so now that I buttered you up, no, I wish. Okay, so yeah, so now that I've won your hearts over, I'll tell you a little scientific story here about the Indian summer monsoon and extreme daily rainfall. So this is entirely observational / reanalysis based, and it's about interannual variability and about rainfall on daily short time scales, right? And so in that regard, it's much more like talks from Jorge and others compared to my previous talks, which were about these zonal mean, time mean sort of stories. Or in the case of the Sahel, at least, a long-term change in season mean and domain average rainfall, right? So sort of we've spanned the whole spectrum across these three talks here. And I've got loads of time since we started 5 minutes early, so. Okay, so the structure of the talk is as follows. It's a three-part. First, just a little bit of extra background about the Indian monsoon, including why we should care about it and sort of the state of current understanding. The second part, we'll be talking about interannual variability in the seasonal mean rainfall in the Indian summer monsoon. And then the third part is where I'll get into the extreme daily rainfall events. Basically, the understanding the seasonal mean interannual variability and its spatial patterns within the Indian subcontinent helps us better understand the extremes. Okay, so the key thing to know physically about the Indian summer monsoon is that it is an intense summer rainy season. So I'm showing here data just taken from Wikipedia of monthly climatological rainfall. Purple is Mumbai, which is on the western coast. It's India's, by some measure, its largest city. And you see zero rainfall, essentially, throughout January through April. And then from May to June, this massive pickup to a climatology, so averaged across all years, in July of 30 inches. So, you know, that's something like probably 800, 900 millimeters, something like that. And then a lot of rain in the June before it, August as well, and September, and then a not as rapid as the onset, but a pretty rapid demise as well into the dry season. You can compare that with New York City, where I live, and our rainfall, our precipitation, I should say, is almost no seasonality. This time of year, much of it falls as snow rather than rain, but with respect to the actual liquid that falls, there's no seasons. And instead, our seasons are all about the temperature, right? So right now it's freezing cold there. 6 months from now, on any random day, you know it will be much warmer. And India is the opposite. There's very little temperature seasonality, and there's a massive rainy season. I think Ciudad de Mexico is more or less the same, right? Much more temperature seasonality, much less the rainy season. Yeah. Just define the rainy season usefully as just the rain falling June, July, August, September, JJAS. And now I'm showing the same climatological rainfall cycle. I'm just using daily data instead of monthly data. It'll be a few slides later, despite the text, where I describe the underlying data set here. And I'll also mention in more detail later, a small part of the far southeast of the country has a sort of a different seasonal picture, but most everywhere is something like this. I do just want to, before diving into the interannual variability and the local sort of things, I do just want to remind ourselves, though, that it is nonetheless a sort of integrally connected to this global monsoon system, right? So this nice little schematic animation from UCAR shows you monthly climatologies of precip on a gridded basis, sort of centered over the maritime continent. And you can see India up here.
you see, so we're in February now, and we come into the rainy season here. So there's that intense rainy season in India, and then it all goes away. But you can also see that that is not so different than much of the other longitudes nearby, right? But that's the last I'll say in the rest of the talk about zonal mean, Hadley cells, ITCZ, anything like that. Okay, so why, as climate scientists, might we care about the Indian monsoon? One reason is it basically is why we discovered ENSO, El Nino Southern Oscillation. So Sir Gilbert Walker in the early 20th century was tasked by the British Meteorological Department in India to find predictors of drought and flood years in India because of the famines that drought years would bring to the subcontinent. And he scoured the records for all the data he could find and ultimately found this strong correlation, or actually, I should say strong interannual fluctuations in the zonal pressure, surface pressure gradient along the equatorial Pacific. And that seesawing of the zonal pressure gradient, it became known as the Southern Oscillation, which is the SO in ENSO. So for fun, I wanted to see just how good a relationship this had with Indian rainfall back in Walker's era. So I'm showing in orange a time series from 1900 to 1920, so around when, of sort of average summer rainfall over the whole India subcontinent. And then the blue curve is negative, is minus the Nino 3.4 index, our sort of standard index of ENSO, right? And you can see the correspondence is pretty clear. The correlation is about 0.6. So it was like signal, this kind of signal is what Walker discovered and led to ENSO, which, as you may know, is sort of the single most important internal variability mode on annual timescales for our world. Okay, extreme daily rainfall in the Grijalva basin or in India can be truly devastating. So this is an image taken from a 2005 flood in Maharashtra state. That's the state where Mumbai is. And in that year, on a single day, they had nearly a meter of rain. And so that's sort of awesome for us as scientists physically, but it was horrific. There were more than 1,000 people that died in floods and other hazards. On the upside, a really wonderful thing about the monsoon rains in India is that they wash out air pollution. Maybe the same happens here in CDMX. So you can see here, this is from the New York Times. This is in New Delhi, which is further north. A time series for a single year of PM 2.5 concentrations. And you see this clear, massive drop. The air gets much cleaner in the summer and then gets dirty again in the winter. The rain is just constantly washing out the air pollution. And then the first time I gave this talk was on Valentine's Day, so I've kept it ever since. In this great book, there's this quote from a poem from many hundreds of years ago, maybe more than that, from a Tamil is in the southeast, I believe, where the poet links romantic love with this idea of the monsoon rains sort of mixing up with the dirt underneath. Okay, so that's sort of just laying out the Indian monsoon. And now we'll turn to the question of interannual variability in the seasonal mean rainfall. And I included this kind of cheeky, maybe obnoxious, depending on your taste, tagline, which was do the most direct thing with the right data. And hopefully that'll become clear what I mean by that by the end of the section. I should say, as with yesterday, questions as we go are very welcome. This is work published in Geophysical Research Letters in 3 years ago now. And this was coming out of a postdoc I did in 2019 through 21 at Lamont Doherty Earth Observatory at Columbia, working with Adam Sobel, Michela Biasuti, and Mark Kane. And on the Indian side, this was through a project funded by the Indian the Indian Ministry of Earth Science. And through them on the India side, we had a ton of help from Sulochana Gadgil, who's a wonderful scientist of the monsoon there. Okay, so the data set we are using is from the IMD, the Indian Meteorological Department. This is a 1/4 degree lat by lawn gridded daily rainfall product that notably spans all the way back to the beginning of the 20th century, to 1901. Excuse me. So British colonialism, for all of its horrors, one major upside was the very fastidious and extensive network of rain gauges and other meteorological observations that they set up. So this image here, all of these dots are rain gauges. Not all of them were active the entire time. They come and go, but we're still talking about multiple thousands of stations over a century-plus time scale. And especially when we get to the extremes, which are inherently noisy, that length of time series is critical for getting statistically significant signals. And basically they just interpolate these into boxes, and then that's how you get from these station networks to a gridded product. The other fields are pretty conventional. The Nino 3.4 index of ENSO we take from the extended reconstructed SST product, again over this 120-year period, 1901 to 2020. And we use reanalysis, not observations, Dave. From era 5, we're gonna look at hourly, daily, and monthly fields over the satellite era, so 79 to 2020. If you ask why we didn't extend this work to 2023 or 2024, is we started this project in 2020, 2019, and it's taken me a very, very long time to get the last of it published. Okay, so here's what we'll do. We'll take the gridded product, you average over all 122 days in June through September, and you can get this climatological, and you average that over all 120 years, and you get this climatological map of rainfall as a function of location within the Indian subcontinent. And we'll go into more detail in just a bit about the key features here. The first, though, what we do is we just chop off pretty much all of the north, so into the Himalayas up here and the foothills, as well as, this is called Northeast India, it's its official name, this part above and north of, and east of Bangladesh. The mask here is from one of Sulochana's papers. We're still going to refer to this smaller domain as just India moving forward. The time series season mean averaged over the 2 different domains, for example, they're almost perfectly correlated. So why do we do that? Is basically because some of the data up in this area is clearly spurious. So I'm highlighting this point just above the Bangladeshi border here. I'm showing you in this slide a time series of the summer mean rain at a grid point there in this data set. And you can see moving right along, and then sometime in the early 70s, things just go totally nuts, right? And you know, it's just clearly spurious. And then it's sort of through the interpolation procedure that then contaminates nearby grid points. And we just can't trust the data in that part of the domain. Yeah, go ahead, Simone.
I was just wondering, the IMD also publishes the All Indian rainfall time series. Is it the same based on the same rain gauges and the same domain that you used?
That's a good question, because I've never used that directly myself. My guess is that it's their whole gauge network, and they probably just average across them before the interpolations step, or maybe not. Maybe they do interpolate to make sure the spatial coverage is uniform. Yes. Yeah, who knows? Maybe they, the partition, right? So when Bangladesh broke off, things like this happened around this time. So maybe there was some revolutionary who stuck some dirt into their records. Who knows? At any rate, we'll focus on this monsoonal India, let's call it, moving forward. Okay, so the average of the summer mean rainfall over the whole domain is a very popular metric. It's very important to Indians. It's called the All India Rainfall Index, or ARI. It's physically intuitive, and it's very easy to compute. It's just an average, right? So this is a particular year, values at each point, the map, 1995, sort of quasi-random rainfall. Average that over the whole domain. The ARI index you get is, for that particular year, is 6.3 millimeters per day. And we simply look at a time series of that here. We do this for all 120 years. So it's a widely used as a metric for evaluating models, right? How well do they capture the Indian monsoon? The first thing you do is, what do they do for, how well do they do ARI? I think there are actual decisions made on the basis of ARI as well with respect to real world things. So it's a very important metric. On the other hand, it's also been the source of some controversy for a long time now. So in a paper in 1995, Sulochana, she'll be my foil now instead of my friend, argued that basically because of the strong spatial heterogeneity there's within the Indian subcontinent, averaging over all of this sort of disparate regions isn't a physically meaningful thing to do. You've sort of thrown the baby out with the bathwater in a sense. And so she actually calls it not very meaningful. And then separately, it's been argued on societal sort of impact grounds that this average is not as important as the extent of wet versus dry anomalies, right? So the more expansive your drought is in area, the more farms will be affected. And those needn't go together, right? Because your rain is very constant. The heaviest rain is very concentrated, and so the anomalous average rainfall could be, in principle, quite different than the area of your dry versus your wet anomalies. And yeah, this has sort of persisted, these arguments, into the 21st century. What's this spatial heterogeneity I'm referring to? We'll go back to this climatology map here. And we see in the color scale, we have from the yellows to the very little rain, quite dry places. So that's the far southeast I mentioned, and up in the far northwest near the Pakistan border, called Rajasthan state, sort of almost a desert. And then you have values going all the way up to above 40 millimeters per day in much of this very narrow coastal band along the Arabian Sea. So this band is hemmed in by the Western Ghats mountain range, sort of right along this sharp gradient. And this very sharp gradient to much drier values to the east over Southeast India. And then we have not quite as high as in this Western Ghats region, but still very high rainfall in the sort of central and eastern northern India, sometimes called the central monsoon zone or the core monsoon zone here. Okay. This is a topography map showing you this sort of influence of the mountain range, just very close to the coast there. You can think of it to reasonable approximation as you've got this southwesterly flow during the summer, sort of impinging almost perfectly at a right angle on these mountains. So even though they're not that high, only a kilometer or two, the very wet, moist air that's being advected over them generates just almost every single day very heavy rainfall. In the central monsoon zone, the elevated values there are instead mostly due to synoptic scale systems called low pressure systems. So these are cyclonic storms that form in the Bay of Bengal, and they track sort of west-northwest over this part of the domain. Excuse me. Each one of the curves in this picture, taken from a paper in 2020, is a track of a historical low pressure system. The green is weak and the blue are strong. And you see that most of the tracks are up here. Very few make it all the way up to the far northwest or hit the southeast India. So Southeast India, where it's dry, their rainy season is actually in the autumn, sort of in the retreating phase, or the northeast monsoon, it's called. In the summer, they're in this sort of anti-Goldilocks zone, where they're in the rain shadow of the mountains, and they're also too far south to be hit by most of the low pressure systems. Okay, so we're trying to sort of get through, better understand this ARI controversy. I recall I mentioned the issue of the spatial extent of dry versus wet anomalies. And so we just create a new index that directly tells you that. Okay, so all you do is for a given year, here's the rain anomaly for 1995 as a function of grid point. And you simply say, where is that positive versus where is that negative? And you count the number of grid points where it's positive, where there's more rain than usual. And that's your index. So in this particular year, 40% of the domain was wetter than normal, 60% was drier. And you do this for every year, and that's your new index. And here I'm showing it scattered, it's in the y-axis, against the traditional just summer mean all India rainfall index here. You see that they're nearly perfectly correlated, 0.96. And so the controversy is resolved, right? Yes, in principle, ARI could be different than the spatial extent, but in practice, they're basically the same, right? So it was sort of a whole big nothing burger, as we say, all along. Why, physically, why would that be the case? Why would they go so well together? To start to understand that, we can do this sort of standard decomposition of the season mean rainfall into the product of two terms. First, the number of days with non-trivial rainfall. So you use a 1 millimeter threshold. If there's more than 1 millimeter of rain, you call it a rainy day. And the product of that times the rain intensity, the average rain on rainy days, right? So how often is it raining? And then when it rains, how intense is the rain? This is showing that schematically for a particular grid point. The brown dots are dry days. The blue is the rainy days. This is the climatology. So the left is just the summer mean rain again. And we have the center here is the number of rainy days. And the right is this rainfall intensity, the rain rate conditioned on rainy days. You see in the southwest and sort of the far central east, you have rain virtually every single day of the summer, and much less in the dry northwest and southeast. And the rain intensity on those days is, again, very high in the southwest, but it's more spatially homogeneous in the rest of the domain. Hopefully this isn't bordering on pedantic here, but just to show you the anomalies for this particular 1995 year, again, for the mean rain on the left, and So we had a good amount of the country had less rainy days than usual. And it's more of a mixed signal regarding the mean rainfall intensity in that particular year. If we now we're looking at correlations between Nino 3.4 and either the mean rain on the left for the summer or the number of rainy days on the right. And consistent, other studies had shown this before us, but the summer mean rain signal you see is brown most everywhere, right? So brown means less with El Nino. So that's consistent with ENSO's sort of well-known since Walker's day drought sort of, or its propensity to bring drought to India as a whole. So El Nino years, you get less rain overall over most of the domain. And it's an even clearer and more widespread signal in the frequency of rainy days. So most of this summer mean drying is coming from there being less, it's just raining less often. And so you could argue that the stronger El Nino is, the more that its sort of drying influence, its reduction in dry days is going to win out over other factors. And so you're just, the stronger El Nino is, the higher propensity you're going to have for a broader spatial extent of dry areas. Why is that happening? Well, basically, the whole troposphere dries and is subsiding in an anomalous sense in El Nino years. So I'm showing you composites, El Nino versus La Nina. This is now from era 5 over the satellite era. The left is relative humidity as a function of pressure. And the right is vertical velocity, omega. You see the entire troposphere, El Nino is considerably drier in El Nino compared to La Nina years. And throughout the free troposphere, at least, you have this strong subsidence over the India domain. So descent and dryness, both of those, whether you think in terms of column water vapor or buoyancy or anything, that's not going to go well for convection. Okay, so now we're making the transition to the extremes. I'm showing on the left now the Nino 3.4 correlation again, but now this is with that rainfall intensity, the rain conditioned on rainy days. And now it's a much different signal, right? So rather than just widespread, everything's brown, we have still decreases in the southeast and mostly in the northwest. But now over much of this core monsoon zone, and to some extent the Western Ghats southwestern band, we actually have more intense daily rainfall episodes. So in El Nino, what this is saying in the regions with blue is El Nino summers, when it does rain, even though that's less often, it rains more intensely. And if you do a first EOF analysis, sort of for a different perspective on, or I should say, a non-ENSO influenced or explicitly ENSO involved calculation, you just do a first empirical orthogonal function computed on this rainfall intensity, you get a very similar signal here. All right, so we defined these regions here to where we're going to aggregate over some of these quantities moving forward, outlined in these sort of dark blue contours. I'll come back to those in just a bit. But this gives us a hint that maybe there's something going on with the extremes, right? So if the intensity on rainy days is going up in much of the domain, in principle, that could be like moderate rainfall events are getting stronger, or it could be that the far right tail, the really extreme events, are getting more extreme. Okay, last thing, this is sort of an aside before turning to the extremes properly. This really sharp spatial gradients, this really pronounced heterogeneity within the subcontinent means that you have to be really careful when you're looking at this from a gridded perspective. All right, so the left is showing from another paper of Solochina's in the early 90s, the sort of rainfall provinces that another Brit, Blandford, even before Walker, used as sort of coherent rainfall zones within the subcontinent, right? And the idea was try to come up with the fewest possible subdomains where the rainfall variability tends to be coherent spatially within that location. And you see that Blandford drew these very narrow sort of strips along the southwest, right? Because of that narrow band. Fast forward 100-something years, and we have satellite data and big advances, but at least the initial products, that's a pretty crude, right, like 2.5 by 2.5 degree boxes that you're looking at. And so there have been papers where, based on big grid boxes like this, try to look into the relationships within the subregions of India and rainfall and ENSO. And suffice it to say, when you create a box like this one, it may, in terms of what's actually happening from the quarter degree, so a tenth or I guess an area 100 times smaller grid boxes, you see that that domain is sort of smearing together two totally different regimes, right? You're smearing together the coastal regime here and the dry sort of leeward side of the mountains on the other side. So with gridded data, not just for India, but in general, you have to be at a sufficient scale to capture the things you're interested in, or you might end up with some errant conclusions. Okay, now we'll turn to the extremes. And the cheeky tagline here was basically just, we were sure we would find this in the literature somewhere, that someone had looked at daily rainfall or rainfall extremes, short time scales, and the ENSO relationship for India. And we never found it. So we ended up doing it ourselves. This is a manuscript that now includes, in addition to Adam, Michaela, and Mark, Destiny Zamir Myers. She was an undergrad at Columbia who worked with us. She found the signal in the extremes initially, actually. So it all sort of stems from Destiny's work. Fayez Ahmed at UCLA and Mike Tippett at Columbia came on later on as well. Fayez, I'll talk a lot about his buoyancy metric that we're going to use a lot. And then Mike is sort of a statistics guru and really helped us work through the statistical significance. Okay, so sort of to start, I'll put in context the interannual variability in the extremes as regards what the community has been thinking about instead. And that's mostly been secular trends and climate change. This paper by Goswami et al. In Science in 2006, extremely influential. And their argument was that they had detected a significant positive upward trend over the last 50 years, 1950 to 2000, in this metric, which is basically some indicator of the amount of extreme daily rainfall within the central part of India. So, and they further made claims that this was the emergence of this was a global warming driven signal. This wasn't natural variability. This was a secular trend that would continue, that it was driven by moistening due to global warming. And they used the in situ rather than the gridded product to do that. And yeah, so that's been a real focus of the literature ever since. Two caveats to that. The first is in the gray text here. There's a nice paper in 2019 by Lin and Hoybers, where basically, because of changes in the network, stations going offline and online, there's a good chance that some of this trend could be specious, could be an artifact of the changing observational network. Someone is calling me. And then the other one is, so this paper analysis stopped at 2000. More recently, a paper looked at, well, what's been happening with extremes in the 20 years since. This is another metric of extremes over central India. And actually, the trends it depends on this specific metric. It depends on where precisely you average. And there's a lot of suggestions that actually the trend has been negative over the last 20 years. Is that just due to internal variability? Is it forced? I really have no idea. But I would just, the point there is to take this with a grain of salt. There may be a warming-driven secular trend already, and it may be the case in the future, but I wouldn't bet my life on it, let's say that. It is the case, though, that daily rainfall extremes in the region do get more frequent in climate model simulations of future warming. So this paper looked at a very high emissions scenario across CMIP6 models. The blue shading is saying that in that grid point, you have more heavy extreme rainfall days. And you can see most of the domain has exactly that. And also that those are concentrated within these two sort of wet regions I've highlighted, right? The Western Ghats in the southwest and this sort of central India box. So we can construct a 2x2 matrix with respect to the time scale, interannual versus secular trends, and then the seasonal mean, I guess another time scale, the seasonal mean versus the daily extremes, right? And where the interannual ENSO question regarding the season mean rainfall has been studied for over a century, hundreds of papers. Secular trends, I didn't talk about those regarding the seasonal mean, but to take my word, there is also very, very well studied. And as I just mentioned, the trends in extremes have been very extensively studied, but we just can't find any like head-on, very systematic explorations of the interannual story with respect to daily extremes. Okay, why care about interannual variability and daily extremes? There's at least two reasons. So comparing it to the climate change problem, even if emissions, God willing, go to zero tomorrow and climate change goes away, there will still be ENSO, right? And so it will matter to people in India no matter what happens with climate change. And then secondly, if there is a clear ENSO signal, ENSO itself can be skillfully forecasted seasonally, right? A month or more in advance. And so then it at least becomes possible that we could get to a skillful prediction of extreme rain occurrence likelihood. Yeah. Okay, the metric I'm going to be using for daily extreme rainfall is one called the cutoff rain rate. And this is a quantity that has been spearheaded by who else but Dave Nealon. The couple papers here I'll highlight to, if you want a sort of starting point to think more about the cutoff. It's very easy to estimate if you make assumptions, if your distribution is more or less a gamma distribution like precip tends to be. The cutoff is just the variance divided by the mean. How to think about the cutoff more physical terms? I'm showing here for the whole domain, aggregating all points, all days, a PDF of daily rainfall, and on a log-log scale here. And in a log-log scale, precip distributions, which as I mentioned, tend to be well approximated by a gamma distribution, have these two regimes. So from very weak to moderate rain rates, you have this nearly constant slope. That's called the power law range. And then at some threshold, the probabilities then instead drop off more exponentially as you get to the really extreme accumulations. The cutoff is essentially just the point that separates those two regimes. that might sound sort of esoteric compared to, say, you know, season daily max or more conventional metrics. We've tried very hard to look systematically at any other possible metrics and other sort of methodological sensitivities, and all the big picture results hold regardless of what your specific metric is. Okay, so this is sort of a big slide. This is the headline result, I would say, is here in this slide. Essentially, very much like that intense rainfall intensity signal we saw, extreme daily rainfall, as quantified by the cutoff in this case, is made more likely in El Nino years and less likely in La Nina years over much of central India and the Western Ghats southwestern band. And conversely, daily extremes are suppressed primarily in El Nino years in the drier southeast and the northwest. That's shown in this map. This is the plot here is the cutoff for each grid point in each year, correlated against Nino 3.4 for JJAS. The black contours, if you could, yeah, I think you can see them. Those enclose regions that are where this signal is statistically significant, and that's based on a field significance test. This is daily extremes are a very noisy quantity, right? There's plenty of noise in this field, right? And you'll notice that much of the domain is statistically insignificant. But I'll show you right after this, when we aggregate over these individual domains we've defined, we get very strong statistically significant signals there as well. So yeah, so just to be explicit about that, we have 4 domains. We have the whole all monsoonal India domain. So I'll use the AMI acronym there. We have this central monsoon zone, blue curve here. This was a mass, this domain, the region definition here came also from a paper by Sulochana, which in hindsight, we would have cut it off. It kind of catches some of this northwest dry part, but it'll work. And then we, in our 22 paper, defined these 2 regions in the peninsular India, this Western Ghats thing in the green, WG, and then the drier Southeast India, SEI, in the bottom. And I'm showing the left underneath those contours in shading is just the climatological rain again, because hopefully by eye you can see the correspondence between the mean rain across all years and the whole season and the ENSO signal in the extremes, right? So, you know, noise not perfect, notwithstanding, still mostly blues. Where it's blue here, it's mostly blue here, vice versa, right? Okay, so now we define, again, this region aggregated sort of perspective. We take all of the grid points within any of these individual regions, and we aggregate them into a single distribution for a given year. And we compute the cutoff for that distribution, and then we redo all these ENSO signals. The left here are the PDFs across all years for these different regions. And you can see this sort of gamma-like shape in each case. The circles here are the cutoffs. We also, I forgot to mention, we repeated all of our analyses on the IMD, also puts out a 1 by 1 degree resolution gridded product. And that's not just coarser, it's actually uses a fixed network in time. So the quarter degree product, it's a temporally varying network. Basically, they're just trying to use all the data that's available, they throw in there. The 1 by 1 degree product, to make it more consistent, it's a fixed network of stations. And all the results are similar, one versus quarter degree. There's nothing noteworthy to say there. So I won't really talk about the 1 degree product much after that. I'm showing in the right now for each of the 4 regions, composite cutoffs for the El Nino summers in red, La Nina in blue, and then the gray is neutral. Pardon? For the whole domain, for the core monsoon zone and for the Western Ghats, we have a clear separation with a higher cutoff, so more extremes in El Nino years versus La Nina years. And basically the opposite in the southeast. I'll basically just skip over this. This is where I'm trying to show explicitly that there's not a huge sensitivity to the metric you use. So if you use an exceedance count at the 99th percentile, if you do that but restrict just to the satellite era, if you use an even higher percentile, if you just look at the block maximum, at least at the big picture scale or degree of accuracy, the results are pretty much consistent. So we're not trying to do something sneaky by using this cutoff thing. Okay, now we'll go from the cutoff to looking at the whole distribution of rainfall and how that changes under ENSO. And to do that, I'm going to use a quantity from Dave Nealon called the risk ratio. So what a risk ratio is you simply, you have an El Nino composite and a La Nina composite. And you empirically, from the distributions over those 2 composites, you just say, what's the likelihood of rain exceeding a given threshold? So my mouse here is at 10 millimeters. So what's the likelihood of rain exceeding 10 millimeters in the El Nino years? And you divide that by the likelihood in the La Nina years. And I'm showing this relative to unity. So by which I mean the horizontal line here at 0, if you're above that, that means it's more likely in El Nino than La Nina. And if you're below that, it's more likely in La Nina than El Nino. Each curve is one of these different subregions. The solid or the thicker parts are where it is statistically significant based on a permutation test, which took a really long time to sort out. And then these little these little vertical bars are telling you the climatological value of that cutoff. So what do we see? We see at low rain rates, so from just above the 1 millimeter threshold all the way to 10 or so millimeters per day, you have significant decreases in the likelihood, right? So this is that El Nino reducing the amount of rainy days overall and sort of weakening the moderate rain rates. But then in the dry region in the southeast, that just continues and just keeps going all the way, pretty much all the way down to the extremes. Conversely, for the whole domain and the 2 wet subregions, once you get near the cutoff, the climatology, then you actually get upticks in the propensity for these events, as much as 60% increase in the central monsoon zone when you're at these really, really high accumulations, like 100, 200, 300 millimeters. Okay, so now how physically is this happening? To understand that, this is where we bring in Fayez Ahmed's convective buoyancy metric I mentioned called B sub L. This is from a 2020 paper of his along with Angel Adames and Dave Nealon. You could think of it as sort of extending the sort of column water vapor perspective, right? So as Dave nicely showed, in the tropics, generally, we have this really strong exponential uptick of rainfall with column water vapor. What Fayez does is creates a buoyancy metric that includes 2 factors. The first is sort of a dry gravitational instability. It's the undilute buoyancy of a subcloud layer relative to the conditions in a lower free tropospheric layer. It's just this 2-layer thing. We'll refer to that as just the instability part. And then a second part is just a moisture, is essentially the moisture part. It's not exactly the column water vapor. What it is a subsaturation. So how much, basically how dry that lower free tropospheric layer is. On the grounds that as a parcel is ascending, if it goes through dry air, the mixing is gonna inhibit growth of that convection and rainfall, right? And in their original paper, what they showed was you get not just a sort of exponential curve, but you get even more of a sort of threshold sort of behavior of rainfall conditioned on this buoyancy metric. And we found that's the exact same for our domains here. So using the daily rainfall data against this convective buoyancy computed from era 5. So now we have to restrict to the satellite era. These are conditionally average rainfall in the solid, and you see basically no rainfall until you get towards positive values of the buoyancy, and then this really sharp uptick in each case. And as sort of related to the self-organized criticality stuff that Dave mentioned, you do see this behavior where the PDF peaks right before that threshold and then drops off. So it seems like the parcels are rapidly consuming that buoyancy once they get to those values. Okay. If we now just look at the whole domain and go El Nino versus La Nina composites in red versus blue, now I'm showing conditional quantiles rather than conditional rainfall conditionally averaged on buoyancy. If it's hard to see the red curves under the blue, that's kind of the point. Basically, the relationship between rainfall and this buoyancy metric isn't itself strongly dependent on ENSO, right? And so that simplifies the story moving forward. We can ask, we can sort of ask ourselves, well, we can understand the extreme rainfall behavior under ENSO by then understanding what the behavior of the buoyancy is under ENSO, right? If the buoyancy goes up, we expect, or I should say, if these high buoyancy events become more frequent in El Nino, then we would expect the high rainfall days to become more frequent in El Nino. And it's not perfect, but to a good amount, that is the case. So the left here, I'm showing the 99th percentile rainy day convective buoyancy correlated against Nino 3.4 on a map basis. And then on the right, I'm just showing again the rainfall signal, the extreme rainfall signal. And you can see that they go reasonably well together, right? This is more negative overall, the buoyancy response, and it's less noisy. But what we're arguing is that it's mostly blue in here in the central monsoon zone. It's at least not brown in much of the Western Ghats, right? But it's brown in the southeast and the northwest, akin to the rainfall itself, the extreme rainfall. How does that, the two terms of this buoyancy, they're just summed together. And so you can look at the individual terms on their own. With respect to the moisture, the subsaturation on the right, within this part of the core monsoon zone, you get a contribution. So there are more sort of near saturation days occurring, and that promotes the extreme rainfall. But over the whole south, the whole of peninsular India, including the southwest, you actually get less very wet days. With respect to the sort of just straight temperature instability, you have, again, in the central monsoon zone, a big contribution from that, and you get more of a contribution there in the southwest. Okay, so then that's great, but then what's causing the buoyancy changes, right? Oh, well, first, if you do a region aggregated risk ratio thing, like we did for precip, it basically tells a similar story. Just for the sake of time, I'm gonna skip over that because, yeah. Okay, so what's causing the changes in the buoyancy? Now, actually, we're gonna turn to this synoptic low pressure systems. This now is more preliminary work, so everything I just presented is in a manuscript under review. This is now a manuscript that we're preparing with most of the work with Yuja Yu, who's a postdoc at GFDL. In short, we think of much of both the buoyancy and the rainfall signal is coming because of changes in the tracks of those low pressure systems I mentioned. It's a busy plot, but the solid contours are the climatology of track density of these low pressure cyclonic systems. The color shading, so you see these mostly happen in the northern India. The color shading is an ENSO composite, El Nino minus La Nina. And so in El Nino summers, you get less tracks in the south, less tracks in the far northwest, and you get more tracks over this sort of central eastern part of India. Not unlike, holding the southwest to the side for a moment, not unlike the rainfall and buoyancy signals, right? This overlaid circles, the blue ones are where you can attribute rainfall by some metric to the presence of a low pressure system. And so that sort of low pressure system related extreme rainfall, if it's a blue circle, it's more in an El Nino year, and in the orange, it's less. And you see that too largely tracks with the signals we see considering extreme rainfall across all summer days. So not whether or not it's related to a low pressure system. And just making the correspondence hopefully clear there. So we're excited about that result. At the same time, it means that thinking purely about the local convective buoyancy is only going to get you so far, right? The convective buoyancy is more the tail, this synoptic scale disturbances, and their tracks are more the dog, right? Why are these tracks changing the way that they are? That's something we're only just beginning to think about. We're just sort of speculating at this point. But Michaela has a proposal in to NSF that's going to hopefully explore that if they give us the money. So the low pressure systems, you see there's less clear signals in the southwest, and that's true in general. The rainfall in the southwest is not so driven by these low pressure systems. So what's causing the increase in rainfall, the extreme rainfall there? Here we're invoking another sort of hypothesis as follows. So in general, in the El Nino summers, you have anomalous descent and dryness, as I mentioned, and that's going to inhibit your weaker convective events, right? They're not going to be able to win out over a drier sinking troposphere. And convection, right, is just releasing instability in some fundamental way. And so if you have less of those weaker events releasing that instability, you're going to have more instability that's able to build up, right? And so then when there's a passing wave or something that sort of gets you some ascent, gets you over that threshold, you're then going to be able to convect even more intensely. There's more instability there that then will lead to more extreme events. That's relatively speculative, but yeah, I feel like there's something there. Okay, so recapping, Indian monsoon is important. We know a lot about it. There's much more to know. El Nino summers inhibit weak convection throughout the subcontinent, and that acts to promote drought throughout the domain. But with respect to the intensity of rain when it falls, you have this sort of mixed signal where the wet regions, you actually get more intense rain. And that seems to, and that intensity signal, it manifests specifically in the daily extreme rainfall occurrence. All right, just a couple of parting thoughts of where we're going forward. I mentioned the idea of seasonal forecasting. We actually took an initial stab at this. So Mike Tippett provided us the North American Multi-Model Ensemble, the NMME seasonal forecast system, multi-model mean forecast of the JJAS Nino 3.4 value from the initialized 1 May, so a month ahead of time, their prediction for Nino 3.4. If you redo the correlation against the cutoff against this forecasted Nino 3.4 in this middle panel, you see it looks still mostly like the case when you're using the actual real-time value. So there's maybe something there. At the same time, when you go into the details of the statistics, it's noisier enough that there's basically nothing truly significant. So there could eventually be something here, but we're definitely not there yet. I think it's plausible that some of these mechanisms, not the low pressure systems are very unique to the Indian monsoon. But the arguments regarding instability buildup, for example, aren't obviously unique to the Indian monsoon. And I think we're excited to look into sort of doing similar analyses for the other monsoons, including the Mexican monsoon. Or maybe one of you can do that, because I don't know when we're going to find the time to do it. And similarly, there are other teleconnection modes of importance, the Indian Ocean Dipole, NAO, et cetera, and you could repeat this whole process for any of those, right? Last thing, ENSO versus global warming. In principle, ENSO can help you think about the global warming signal, right? So El Nino is warm overall compared to La Nina. And so can you use what happens with respect to ENSO to think about what will happen in a CO2-driven warming moving forward? In some cases, that's plausible. I think in the case of this question, extremes in India, I just don't think it's there. The warming-driven increase in extreme rainfall is mostly invoking the arguments for explaining that. You're mostly invoking just this mean moistening of the troposphere because of this fixed relative humidity Clausius-Clapeyron thing. We just don't see that at all in the India ENSO story, right? We have drying of the troposphere in the mean, both in terms of specific and relative humidity. And it's this sort of gravitational instability thing that's winning out. And you have this shifts in the low pressure systems that are a big part of the story. It could be that CO2 warming gives you a similar shift, but I don't have a compelling argument for that versus something else. So yeah, I guess to end it more positively, I'd say more work to be done there as well. And yeah, I'll stop there. Thank you.
Great. So now Spencer has been officially banned from the UNAM. Yes, bueno, nada más algo en español. Es importante decir que Norteamérica quiere decir México, Estados Unidos y Canadá. Pero los mexicanos dicen, Norteamérica es pinche, bueno, Estados Unidos. Entonces, pues entiendan eso. Ok, bueno. Voy a leer de mi paper para que vean que realmente creo lo del Mexican monsoon. Perdón. No bad words, nothing.
Está bien.
I'm sorry. Okay, so yeah, questions now? Oh, okay.
Thank you. Nice statistics work. So just I want to have I would like to be like the evil lawyer with the people, agronomers.
Right on.
Why, or have you ever tried to use only extreme daily, only extreme days or extreme values above the more than all the distribution functions, just all the extremes, and then do another distribution with only extremes? Because I have the idea, I guess, that maybe it's a really wet subcontinent that mask the drought.
I'm sorry, I'm not sure I follow.
Yeah, I mean, when you do, since you do the index, you consider all all data. Why you don't usually use extreme data?
Oh, so with this,
Yeah.
you're talking about the index about whether it's raining or not?
Mm-hmm.
Yeah, yeah, you could in principle, you could make the raining versus non-raining, we use a 1 millimeter threshold. You could make that higher, right? If you're wanted to focus on more severe events. We haven't. Yeah, it's a good question. At what point yeah, how different that relationship with the All India Index looks as you're restricting to more and more extremes. Yeah.
Maybe you could see another signal. No, I don't know. It's just an idea.
Yeah.
Jorge?
Thank you, Spencer. I promise I was here for the whole talk. So I didn't miss it. At the end, I guess I was maybe confused. Or you said like the comparison is because El Niño is warm. Would that tell us something about future change? But does that include like this whole Richard Seeger thing of like the pattern effect and whether we go to more El Niño like, La Niña like? Is that what you were saying, or was that not?
I see your point. No, so when people talk about like the ENSO analog, I think they're more generally referring just to a mean warming, right? So on the tropics wide basis, El Nino years are warmer than La Nina, and so it's sort of setting aside the question of the pattern of SST warming under climate change, right? Yeah, it's more like sort of you could think of it as like what's the uniform component of the warming signal? Can you learn from ENSO something about that? And that the response to mean warming for any something like extremes could be the most important signal, or the pattern of the warming could play a huge role too. So
the other thing with the seasonal forecasts, I saw you were using just the raw forecast, right? You didn't do any of Mike's fancy calibration stuff.
Yeah. I think Mike, as I recall, he provided it to me, but it was just the straight mean across the different NMME models.
Yeah, because I think he's found that fixing the forecast probability can change in terms of predictability and prediction skill makes a big difference with not just mean but extreme precip. So maybe that would be something.
Oh, nice. Okay. Yeah. Okay, let's.
And finally, just you said you may want to do this with the Mexican section of stuff, but we definitely don't have thousands of stations. We were colonized by someone else, so we don't have the fancy. So yeah, I would be skeptical.
Yeah, fair enough. I mean, I should say if you restrict to the satellite era, the signals mostly the rainfall signals also hold up. So that's a temporal issue, not a station coverage issue. But yeah, fair. Yeah.
Any other questions? Oh, I'm sorry, Adrian.
Just wanted to come back to this mechanism that you mentioned towards the end of your talk about the suppression and the increase of basically the instability. Were you referring almost to a kind of a increasing cape, or are you purely talking about the moisture there? Because I mean, from the weak temperature gradient approximation within this region, I mean, if you've got enhanced precipitation in the northeast, I mean, that would stabilize the atmosphere right over the whole Indian area. No? So I presume there you're only talking about the impact on the tropospheric drying there. Is that right? It kind of almost alludes to the kind of aggregation argument, that you've got more systems in the northeast, and so things are kind of compact and this area becomes drier. So is it just the humidity you're referring to then? Because the way you described it sounded like a kind of build up of cape.
Yeah, that's more along the lines of what we're thinking about it.
The gradients in free tropospheric temperature are going to be very small, no, across the Indian subcontinent. So I can't see how you can invoke an argument that basically relies on an increase of cape through cooling of the troposphere in these regions that are quite close by each other, where weak temperature gradient should probably prohibit that from happening. That's why I was wondering exactly what you meant from that mechanism there. I was kind of assuming that something was going on there. It's going to be tied much more to the lower tropospheric water vapor, for example. But we can talk about that offline.
Yeah. Yeah, I'd have to think about it more. Yeah, let's talk more about it.
Okay. The other question, so then I'll pass the microphone, I promise, was in the northeast. I'm sounding like Mr. Circular this week. When you looked at the buoyancy metric and you split it up into the two parts, now you have the part which is kind of basically sensitive. It's kind of like your entrainment. You can imagine it like an entraining plume, and you have the moisture term. Again, just playing devil's advocate, as we saw earlier, you know, the convection moisture relationship is a two-way interaction. No? So basically you have a local moistening, but then that also then makes the atmosphere more conducive. So this buoyancy metric BL, I really like the paper, but what it's looking at there is it's saying, okay, a moister lower troposphere then gives you this bigger BL. But again, there's a little bit of circularity in there, because if you've got more of these systems going through, you expect to have a moister atmosphere in that area. So again, in some ways, it's also partly built into this, that the buoyancy term itself is just detecting the fact that there's more convection there, and then you use it to say, oh, we expect more convection there. So again, kind of comes back to the point I made earlier in the week, though, that there's a little bit of circularity in there that we have to be careful about, simply because the convection water vapor relationship is a two-way interaction, and it's not just from one side to the other, if you see what I mean. It's not just the water vapor enhancing the possibility of convection, but the fact that there's more convection there can also then increase the...
Yeah, I get it. Could you, like, looking at a lead lag relationship be a way of trying to disentangle that?
Possibly.
You know, the subsaturation the day before kind of thing?
Yeah, it was just, again, it was just a comment about these correlation maps. If then, you know, that would get around that, but it seems that there's a little bit of, again, circularity in the argument of that.
Yeah, I totally get it. It's a good point. Have you ever talked to Fayez about that?
No, I haven't had the opportunity.
Okay. Yeah, thanks.
Very nice talk, Spencer. So one question, you brought up the IOD towards the end. And the relationship between IOD and El Niño, La Niña is quite an intricate one. They are not independent. And so I was wondering if the IOD signal has been removed or not from your El Niño.
No, yeah, this is just straight Niño 3.4. We did IOD, we did some preliminary analyses now a few years ago on conditioning on the IOD, and it looked not unlike the ENSO signal. So to your point, I think, but they were weak. So
because there has been some discussion in the literature as to how the phase of the IOD, which in general is well correlated, right? You tend to have positive, negative, but again, the phase of the IOD can also modulate the El Niño monsoon relationship on average. Yeah, not again, because the impact on extremes has really not been. So I was wondering if there is a signal there that might make your analysis a bit more clear or not.
Yeah, I think, as I recall, the way it went was the original grant was specifically more direct, supposed to look at it, and so IOD, and especially the atmospheric sort of component or sort of counterpart to the IOD, what's called equinu. but then we convinced ourselves that Equinu isn't actually real.
No.
But so then
I'm
we,
also very skeptical about that.
yeah,
that word.
so then, so then we did these initial IOD composites with respect to the extremes, and then the signal was weak, and then that got us, did a little bit of digging into the literature and saw how complicated or how related the relation, that there is a considerable relationship between ENSO and IOD, and it just started to get complicated, and then we just, so I guess then, as I'm saying that, I have to say that was being a little cavalier in the text, that we just apply it to IOD, to the other teleconnections. It's not quite so straightforward.
And then going back to your the preliminary work, maybe I missed something in there, but where you are looking at changes in the low pressure system. So first of all, we're talking about a very few storms a year.
Yeah,
right?
less than
Not
10. It's like
10? I thought we were talking about
like less than that. Like
less, right?
yeah.
4? Yeah. And then the other thing, the causality here, I'm a bit confused about the causality. So are you saying that it's the low pressure systems that set the right environment, or are we just looking at the fact that at the end, those storms bring a lot of rain, and so you're just looking at intense rainfall associated with those systems? So I was, again, maybe I missed something in
No.
but again, I'm a bit confused about the causality there. So
I skipped the step entirely. So there you just done less directly, but Kieran Hunt's led a paper that we're mostly leaning on, where he's doing composites of many things, sort of LPS centered, tracking individual things and doing composites and doing El Nino versus La Nina. And but regardless of the ENSO part, these systems have very buoyant and very moist cores, right? And that's where the rainfall is most intense. And so the step I skipped over out loud is we're sort of equating that the track movements with movements of those very buoyant, moist cores with them. And so that's how I'm going from the buoyancy maps to the track maps.
There's actually a short question online. Actually, we've been very lax. Do you mind if I ask it? Somebody on the chat on the live stream asked then, basically, do you mean at the recent epoch, the extremes over India are decreasing? So I think what they're asking about is the fact when you showed those trends and you put that lower trend, do you personally believe that there is some kind of significant trend there in the later period? That's what they were asking about.
Yeah.
How robust you might.
Yeah.
Gut feeling from your analysis that kind of recent 20 years is.
Yeah, I don't know. 20 years for something as noisy as extremes. I feel like it's a pretty tough. I forget from that paper how statistically significant by whatever measure they were using that was. ENSO at that time scale, right? If you ended up with more, insofar as there's an ENSO signal in this stuff, which we're arguing for, if you had more El Ninos in the beginning than the later part, or vice versa, that could be a contributor, right, on the interannual with it coming from a natural source. So I haven't thought carefully about it. Yeah, but in general, 20 years trends is tough. That's a tough game to play.
Okay, yeah, I was going to say actually before Alejandro, is that, yeah, considering the occurrences of these low pressure systems, thinking kind of the Alejandro Wheeler-Kelades models, maybe there might be some larger scale waves that occur more frequently in El Nino or La Nina that might be associated with the occurrence of those storms, right? That's the idea. No, I'm just saying that. I also realized that, yes, Adrian and I are twins separated at birth. I didn't talk about this in my talk. I'm more self-promotion here. But also another paper I did with Nealon and with Lintner and Skiro, we do talk about the vertical structure, which is also critical of water vapor, not just the column water vapor. So anyways, but if you're interested, I'll say. Also, my student was on that. My student from Brazil was on that paper too. Okay.
Thank you for your talk. I guess I'm going to ask something really, really off topic, but I'm very curious because you mentioned that you were studying previous works about if somebody has previously studied ENSO and extreme events in India. So I was wondering, I'm not aware of the complexity of the scientific literature in India, but India is a very complex country or very complex continent, not only talking about rainfall, but also cultural, because we can feel like a room like this with people from India, and it's very probable that not each one of them speaks the same language. So I think that was really hard, really very difficult work to try to find anything in the literature if you are dealing with several different kind of languages. Quite interesting. So I was wondering, how was that process?
Um, maybe. I mean, there's also not everyone speaks English, but there's a very large sort of English. I don't know how to call it, penetration across India, right? So I don't. Yeah, what you're describing is true, but I don't. I don't immediately see why that would be at play here. If I had to guess, it's more the same as happens in the States and maybe in Mexico as well. More just sort of the phenomenon of there's a paradigm that's popular and folks stay in that paradigm, right? So there's a popular research strand about ENSO and the season mean rainfall, and so folks work on that problem. And then thanks to the Goswami paper, there's a new paradigm about the trends and extremes, and so then folks pursue that paradigm, and that's just inevitably how science works. But then sometimes that can lead to, in my case, an opportunity scientifically. Yeah.
Yes, I was meaning like it's probable that in some language it could be something related with that, but it's very hard to track the literature in hundreds of different languages. So that's
Yeah.
what I mean.
I think pretty much all the academic literature there is in English.
Yes.
But yeah.
Yeah, perhaps some of people that us from India. There are a few ones. Maybe
Yeah.
might have some information. They can contact Spencer, perhaps. It's quite interesting to learn about different kinds of science, different languages. So it's very hard to track. There are so much complexity, but it's kind of interesting. Yeah, and another thing is I want to fight with Dave. So you say that here people from Mexico say it's not Americans from the United States, but in the United States, everything below Rio Grande is Mexico. So, so we are Thai.
Okay. So I guess the idea would be to get some lunch now, but I wanted to say let's see Temo and Adrian will, after maybe eating some food, we'll go up to the sala audiovisual para que vean bien, ¿no? And then who else is on the hands-on? Is there anybody else? Simona, no, not really. I mean, actually there. And I thought that somebody else was doing something.